All right. So we are live for the Synacor challenge. And today should be the last day for real this time. I thought that the last two times. But let's go over what we did last time. So this is more of the same. We're still on the same two puzzles. But what did we actually do? So we in the Ackerman function, we did reverse engineer that properly. What books are we hitting? Well, we're gonna hit up Wikipedia. So books in a, hitting up to books in a manner of speaking. Um, because it's got what I need to properly optimize the Ackerman function implementation. So we reverse engineered the Ackerman function from the bytecode in the VM. Turns out it has a different constant. Need to find the correct R8 value for that constant. So we figured out what we need to figure out for the Ackerman function. And then we were doing the vault puzzle. Narrowed down vault puzzle ranges. And let's see, we determined that the state space is small enough. State space small enough not to use any yeah, for brute force. I don't know. We didn't really need any optimizations. And well, we didn't we didn't get to the actual goal because we were filtering out the goal. Accidentally prevented reaching goal. So we were filtering out the goal explicitly, like just the goal state. And that bug is found. So for today, we're going to open the vault. So we still need to do this. We're working on that. This is no longer necessary. So I'll just X that off. We haven't done this in the general case, but we've done it as much as we need to. Functions independent from, yeah, we don't need this anymore. But what we're going to do today, is optimize Ackerman function with constants, with constant R8 value. This time for sure. This time I'm gonna pay attention to Wikipedia. There's some good stuff in here. Yeah, I think we go straight to the Ackerman function. So we're last we were here. And I don't think memo is actually gonna help us. So I'm not gonna bother having a memo implementation here. But we do still want to optimize. So I'm gonna leave that there for now. And we're gonna take a look. Well, what I wanted to do is take a look at various values of the Ackerman for like various values of n. Just go like 1 through 10, look for the pattern or whatnot. Well, it doesn't help in this way here. I don't think so. Right? I mean, there will be repeat. It's not going to help us enough. Is what I'm getting at there, right? It's not going to help us compared to like, okay, it could help on top of anything else we do, but if we look at values here, it turns out there are some closed forms, right? So let me expand the Wikipedia page here. Oh, nope. And that's too wide. Let's look at the view. Um, Hold on. There's a tool here to make this view not completely widened. I guess if we just do it in a private window here, it's gonna go back to the defaults and not be too wide. There we go. Okay. Um, so with the plain old Ackerman function, for the values of 1, 2, 3, we do have a closed form. So this is for the m value, right? So when m is equal to 1, then we scale, it's just n plus 1. It's just a successor. And then here, it's the same thing. It's still linear. And then we move on to, well, actually, 2, 3, 5, 7. Here, in fact, it's still linear. Then you move on to like a 2 to the n. No, I thought there was an n squared in here somewhere. But the point is, like, up until 3, there's a closed form for values, right? Um, so if we can figure out what a closed form is for an arbitrary R8, then we can quickly compute all the 3 values. Then when we do 4, it's going to rely on the 3 values, right? So like when 4 is expanded, um, does it actually go up to 5? I'm not sure about that. Here's an expansion. So here's like an expansion of A43, right? So 4 drops by a value, and then the right side of that blows up. So here A42 blows up a bit and comes back down eventually to this nested A3, yada yada. But we never get like an A5, right? So if we have closed forms for all the A3s, then we should be able to compute A4 by running basically these closed form calculations instead. Um, and that's one way. I've had other thoughts. Like it is a smaller domain, so maybe there's something there where like values eventually cycle, or I'm not sure, or like some sort of caching might help a lot there. But I at least want to try a hand at finding these closed forms. Um, so let's test out some implementations here. So let's start with the basic Ackerman. I want to see these closed forms in action. Let's delete this brute force. I don't think that's ever going to be viable. And 1, 2, 10 dot for each. Let me do. So this is going to be our n value, right? So we do acc mn. So in this case, let's say acc is 0, and we'll just print line that, line that. And let's do that for different values of m, just so we can see it in action. And yeah, even for 3. Oh, we don't want to print line that actually. I think what we'd rather do is map and then make string. Yeah, so let's map that. Put an underscore there. we map dot makes string with a comma. A space is fine for me. And we'll print line each of those cases. Okay. So in the case for 0, we have 2, 3, 4, etc. For 1, it's also just a +1 function. Um, for 2, we're getting +2, so this is the line 2n. And for 3, this is n squared. This is some factor of n squared. So let's figure out what that is. I'll let this live here. Okay, so first thing we can do is just start hard coding some of these and seeing that it's still the same. Let's make ack opt. This ack int. What is this? This is a generalized. I'm just gonna delete that for now. I don't need it. Ice Cold Witch, hello and welcome. Okay, so we're gonna rename this ack opt. Sure, yeah, it's our optimized version. And we're gonna add a line for 1. And in the case of 1, it would be n plus 3, right? So this is 0. No, I'm going 1 to 10. I actually want to go from 0. Let's start with 0 there. Okay, so that's actually +2, n plus 2. Great, and let's do the 2 case as well. So here's 1. So this is 2n plus 1, right? 2 times n plus 1. Okay, let's take a look at that and see if we get the same values. Well, I mean, not exactly the same values because, oh, also, it's just wrong. It's straight up wrong here. So let's comment that out. Let's get both our cases here, and we'll want to compare some of these. So we're going to compare the normal Ackerman here with the optimized version. And we can just comment these two out. So for the first 2 lines, okay. So that looks good. Cool. We can get rid of those. And now for the third line, in fact, let's comment that all out. Three, 5, 7, 9. Okay, yeah, that looks good. Okay, now to work on the third line here. So we're gonna have ack with 3 and ack opt with 3. Okay, they're still the same for now, but we haven't started optimizing it yet. Oh, hold up, hold up. The second line is not complete. That was commented out. Okay, so I'm gonna uncomment this and see what we're actually getting. Okay, so it's 2n plus 3. I think plus 3 is what I said, and I wrote 1. Okay, cool. And the 3 case, we could figure it out, but I want to save time. So let's look at the what Wikipedia has to say. And over here it is in the general case. 2 to the n plus 3 minus 3. Oh, it's not even 2 to the n. Like it's 2. Wow. Yeah, it's 2 to the n, and n is scaling. There's always seems to be an n plus 3, though. It might be that plus 3 part that we end up changing. Okay, so for the 3 case, we have 2 to the n, math.pow, and we've got 2 to the n plus 3, right? Dot 2 int, and there's a little minus 3 at the end. Let's give that a shot. Oh, right. Okay, cool. That's working. Now I want to see what the time is like if we do 4. So I'm not going to go very deep into 4. In fact, let's just stick at ACK 4.1. 4.1. That's as far as we'll ever have to go. And ACK opt 4.1. I don't think we need to actually time it. We can probably just see. We can probably just see how fast it runs. Oh boy. Already Stack Overflowing. Oh, come on. I don't want to have to make this a stack-based while loop here, but we could. Um, hmm. Yeah, I thought I'd been able to run Ackerman 4.1 here earlier today. So let's see. Let's set the stack size explicitly. And we could, that should be enough, right? That's increasing the stack size of something we were able to run before. So if that's not enough, then maybe it's that stack size is not actually being applied. Okay. Oh no. Well, you're here now. Um, so what we're doing today is making this, we're optimizing Ackerman by turning this into a closed form here. So it turns out that there's a closed form for like specific values of m. Up until 3, it doesn't get too crazy. Beyond 3, it starts to get really crazy. So I don't think we'll do a closed form for the 4. But if we at least have this optimized, and we can figure out how to optimize it once we stick in R8. We still get a Stack Overflow for just plain old 4.1 though. So let's try our optimized 4.1 and see if that runs. Okay, cool. Well, we already see the optimization in action. Let's see how far we can go with this. Let's say for 3. Cool. We're able to compute that big value pretty quickly. It's a lot faster than what we were seeing before. Um, all right, all right. That I think is going to help out a lot. Um, at this point, I think I can just rename ackopt to ack. We're going to stick with that. We have no reason to test the old version. So rename that to ack. But here's the thing, though. No, we do still need the old ack because we need to figure out how to fit in R8. So R8. So there needs to be an R8 passed along here. R8 is actually going to be this constant here. Replace that 1. And we'll pass along that R8 parameter. And then at this point, we can default it to 1. Yeah, unused stuff. So let's try some small things there. Print line. Oh, you know what? Let's do this. We can do R8 equals 2 and see how that affects these first few lines. So we have act 1, 2, and let's not worry about opt for a minute. We want to compare each of those. We want to compare each of those with an R8 of 2. R8 equals 2. And I hope those don't blow up. Okay, it seemed like that was identical in that case. That makes sense, actually. Okay, here, it just becomes plus 2. So act 2 opt. I'll just note it here. So in the 1 case, in this line, we do another 1. So this becomes plus 1 more, n plus 3. Or in terms of R8, it's n plus 1 plus R8. And let's see, the third line here, this is the 2 case. This had been 2n plus 3. This seems to be, it's still linear. So 5 to 8, 3, 8 to 11, 3. Yeah, so it's 3n now. So in the R8 equals 2 version, we have 2 times, or no, 3n. 3n plus what? Plus 5, it seems. Yeah, 3n plus 5. Okay. And now how do we write that in terms of R8 for both of these? We have 1 plus R8 times n. Yes, exactly. 1 plus R8 times n, right? Because that becomes either 2 or 3 in these cases. Plus this seems like it could be 1 plus 2n? Okay, interesting. Um, yeah, 2n is 2 in this case, plus 1. 2n is 4 plus 1 in that case. Okay. Let's try. I'm going to plug in those lines and check that that still works. Check that our strategy is working, and then we can try line 3 here in a minute. So I'm going to adapt act opt so it has an R8. So R8 int defaults to 1. So this is n plus, we'll make it R8 plus 1. N plus R8 plus 1. And the top one is still n plus 1. Cool. And this case here is going to be R8 plus 1 times n plus 2n plus 1. Okay. So I think it's fair enough to test this by running just the 4 1 functions here. Oh, but we need to, we need something to run it against. Well, let's still at least see if we get the same values, even though we plugged in those functions. 65533 and 214. Yep, that's the same number. You're here to learn the actual math behind this. Good, good. How much have you caught of this so far? Because, just tuned in. Okay, so it's a good time to do a recap because we need to make sure we know where we're going here. Right, on the Wikipedia page here, turns out that there's a closed form for these functions, right? So at first it's just plus 1, and then here we have a linear function, just n plus some constant. And then here we have 2n plus a constant. And then here it becomes 2 to the n, where n might have, 2 to the n plus a constant up there, right? And then from 4 on, it gets crazy. So I don't think we need to implement this because we only need to get 4, 1, right? But it turns out doing just that, where did I have it actually? Here. Yeah, just for the first 3 lines has worked out just fine. And now from here, what I've done, this is a little bit of guess and check. But what I've done is I've re-expressed this function. Well, I've compared the values, the output values, between R8 set to 1 and R8 set to 2, right? And it turns out like the functions are still similar. And I've used that similarity to determine like how to get that closed form in terms of R8 in such a way that works for both R8 equals 1 and R8 equals 2. So you've got that for these first 3 cases here. So I'm about to test it out and see if that's, well, I did just test it out and that still works. So I think we're on the right path and we can do the same kind of thing for 3n. I thought about other ways. I don't know the derivation of that closed form, but like you'd kind of squint at it and be like, hey, this is growing at 2n squared or whatever. But I think actually part of the history mentioned here. So like there's the Ackerman function that we use, and I think that was like a simplification after the fact. Um, where's the Ackerman function? Right, this is the one that we use, right? And we can just do it all in terms of like plus one or whatever. But I think initially stuff like this, it was intended to be okay, let's scale up from addition to multiplication to exponentiation, and at each level it does the exponentiation. What comes after that? So I think just by seeing the history, you'd be like, okay, well, it's supposed to be like that. So like there is supposed to be a closed form then. The big up arrows, Shiification, Shi. Yeah, something like that. So this is working so far. What I'm gonna do now is compare the values from line 3. So so we just did this for line 2. I'm gonna copy paste that. We're gonna compare line 3. Um, and this is for the plain old Ackerman. I think I just use opt for both of these actually, because no, opt is specialized to R8 equals 1, so we can't use opt. And let's hope this doesn't blow up. R8 equals 2. Ah, fuck it, already blows up. Okay, instead of 0 to 10, let's do 0 to 5. That's enough for us to figure out the pattern, right? Okay, great. So this is with R8 equals 1 up here. And that was a 2 to the n. Yeah, 2 to the n plus 3 and then minus 3. So here, hyperexponentiation. Fair enough, fair enough. I mean, you can square and then you can cube and then hypercube it, tetration, right? Tetration is the next step after that. So yeah, hyperexponentiation. That makes sense. Um, okay. So let's try to get some values there. Let's open up my ACK worksheet. I'm gonna bring this in with me. And I don't think we care about all this other stuff we were working on before. I think it's nice to have an Act 2. No. We don't need that. Hmm. Okay, so let's try this out for a few values. Um, so val n equals, well, no. We'll just put some straight raw expressions here so we can keep them in line. Um, so this is the 0 case, right? And then we have the 1 case, and that should give us 5 and 13. Oh, I mean, if R8 is equal to 1. Oh, hold on. This is the wrong line altogether. Okay. So when n, we'll just set n. When n equals 0, that should be a 5, right? So we want to express this whole expression in terms of R8. So what happened in the previous ones? The base case for this was supposed to be like 2n plus 3. And I'm guessing it will show up in here. So let's do like math.pow of 2 and 0. Well, it's got to be something. The 0 case might not be enough for us to figure this out. So let's try this again with n equals 1. Okay, so this gets us to 13. And this is 2 to the third, or 2 to the fourth minus 3. So 38 then is 2 to the something minus something. So we can just kind of search around for that. 2 to the I don't know, let's try that number's too big, right? 64. The minus something could also be big. But let's at least look at values that are sort of aligning in there. So we have n equals 1. We'll say 1 plus 5 here. That seems reasonable-ish. We have 2. Let's do 2 plus 5. 128. That's looking reasonable. Let's see if that keeps staying reasonable. So 3 to the fifth. 256. Well, that's falling behind. Okay, it could be. Geez, would this scale with n? Hmm. Well, what happened up here? So the right side here starts scaling up with n too. So the thing that looked like a constant at first, it was 2n plus 3. The constant started scaling up. Um, is this even accurate? Was this accurate up here? Let's pull up the Wikipedia here. So we had okay, 2 to the n plus 3 minus 3. That's what's going on there. And I'd shortened that down to 2 to the n, and I'd moved that constant in. So leaving that n plus 3 might have made this make a little bit more sense. Let's rewrite that and see if that works better that way. So we'll start by writing down the expression that they had. So they had 2 times n plus 3 minus 3. Okay, and to generalize that, geez, what is our expression for 2? In 2, this simplifies down when R8 equals 2. R8 equals 2, then we get 3n plus 5. Right. So we went from 2n plus 3 to 3n plus 5. So in this case here, we go from that, and how do we make that work out to plus 5? So n in terms of, well, let's start by making that in terms of R8. So 2 plus here is going to be R8 plus 2. R8 plus 2. Okay, so in the 2n case, that becomes and we'll just write it out. So in the 2 case, that becomes 2, yeah, 2 times n plus 3 minus 3, right? And that expands out to, well, okay, we're just actually redoing the work we did earlier. That expands out to 2n plus 3. Yeah, that's not what we actually want to expand. So let's expand the R rate. 2 times, or the 3 case. Let's do the 3 case. So this becomes 2 times n plus 2 plus 2 minus 3. Aha, that's nice. So this actually becomes 2n plus 4 minus 3, which is 2n plus 5. 8 minus 3, 5. Okay, great. So I don't think we want the form I'd written up there. We just want 1n, and we get 1n by doing it this way. So we'll delete that. Okay. So if we express this, then let's express that in terms of R8. So this will work for the 1 case. If we, what's this, R8 plus 2? R8 plus 2. Okay. So R8 plus 2, 3, 3, 5, 5. Oh, that is sort of what we're doing here. But the right-hand side? No, that still isn't handling the right-hand side. N equals. Okay, so we want an 11 out of the 0 case. So let's do something 2 to the something. And that something should depend on both n and R8, right? Normally it's just n plus R8 plus 2. So 1 plus 2 plus something should equal 11. And then we have a minus. So it was minus 3. I think that 3 is probably going to scale 2, though. What if it is 2 to the 4th? Well, like, what if it's 16 minus 5? Wait, so 1 plus 2 plus 1. 2 to the 4th. Yeah, 2 to the 4th is 16 minus 5. So that works. Cool. Now let's just try something similar for the other numbers. So here we're expecting 38. And what increased? N increased. So we do 2 plus 2 plus 1. And I think this is where we realize that this constant factor here depends on n too. But we'll see. So we have 27. And in this case, that is plus 11. 11 kind of feels like a promising number. That seems recursive. That's the previous answer, right? I don't like that it's plus. But that's how we get there. Let's see if you notice. We're going to keep running along with this pattern here and see if we notice some pattern in the constant that we're adding. So 3 plus R8 plus 1. You know what? We'll say R8 equals 2. And we'll replace those with R8 so it's more obvious what we're doing. R8 plus some constant. Oh, hold up, hold up. Let's back up. Well, let's keep that there. This is supposed to be the 0 case. That's what we actually printed. Let's go back to our Ackerman. Yeah, it's 0 to 5. So if this was the 0 case, this n is actually 0. So that's 0 plus R8 plus 2 to make that work. And this is the 1 case. 1 gets us 38. And then 2 should get us 119. All right. So in this case, what's a constant? It's naturally 32. And we need to get 32 up to 38. So this is plus 6. My fear here is that this plus 2 will also scale with n. But we'll see. We'll see. This n plus 3 definitely does look like plus R8 plus 2. Okay, so let's look at this third case. We're trying to get 119. 119. This was supposed to be 38. Well, we've already got it. 64. We need to add quite a lot. What's that? 119 minus 64, 55. Plus 55. Well, does it keep up at all? Right? Does the big factor, like this is going to be the big factor, no matter what this is, does this big factor keep up? If it doesn't keep up, we'll have to change this plus 2 and make that scale, I suppose. But if that scales, then this won't work here. Unless it's like 2 to the 0 kind of a situation, or 2 to the 1, right? This could be um, 1 plus 1 to the 1 or something, right? And that's why it's always the same. Or to the n. No, yeah, and 1 to the n wouldn't change anything, right? If that is like R8 to the n, that's a case where like that could actually, this plus part could scale. Um, yeah, let's just plug in more values. So for 3, 4, and we have until 5. So let's see what those values are and see if it's at all keeping up with what's expected. So here we're expecting 362, 1091, and 3278. And if this isn't working, what we can always do is open up the Wikipedia page and go kind of back to the math. Look at how this is even derived in the first place, and then try to derive it for this. Right? If we can't kind of like guess at it or try to fit, and if we can't fit it, we can always go back to deriving it. It seems like, are those off by factors? Right, if this was 3, it'd be insanely too huge. No, no. Right, it's just another multiplication by 2. But, I don't know. The slowest growth we could get here is like linear, right? So that would be 3, 4, 5, 6, 7. At 7, that's going to be multiplying by like 2 to the 5th. So that's going to be huge. Yes, I don't think that does scale. Great. So we try to find a pattern in the constant to the right. I hope. I hope. Okay. We'll figure that out. I'll be right back. Gotta use the bathroom. All right. I thought last Tuesday was the last stream, so uh, I'll see you here tomorrow. This feels tractable though. I think we're making actual progress. uh, but I know the stream knows what actually happened. No, this is the 29th. Yesterday was the 28th. I didn't even write. Yeah, this is the 28th from yesterday. Um, yeah, for part 7, we were basically still doing that. The vault puzzle and the bytecode extraction for the Ackerman. Um, no, that was part 8. Jeez. Well, you can see in the log, we've actually that's been on our to-do list for a while. So this is the last time we actually made some real progress. And then it's kind of been these same two puzzles. But let's not dwell on that. Because this seems like real progress here. Okay, yeah, we're having powers of 2. This is increasing roughly by 2. It looks kind of like it's multiplying by 3 every time, actually. It kind of looks like it's multiplying by 3. So maybe this is 3 here. That's where it scales. All right. So what if this is supposed to be R8 plus 1? R8 plus 1. 3 to the something. And maybe that something has something to do with R8. So let's see what values we're getting. Well, okay, that's too big to start. How do we get... Yeah, this whole thing here is too big. So this had been n plus 3. So it's going to be something gnarlier than n plus 3. And if we have 3 to the something here for the 0 case, that's already 27. But there had been a minus 3. So in this case, it's 27 minus, what is that? 16 to get 11. And then to get 38. Okay, it's kind of like this thing is one step ahead of us, actually. So here's n plus 3 here. But let's just verify this. So like 11 times 3 is 33, right? 38 times 3 is 114, just 5 short of there. Um, and 119 times 3 is 357. Oh, wait, we're seeing the pattern. It's always plus 5. So it's always like times 3 plus 5, the previous one. Um, okay, so we have 11. We have 11 times 3 plus 5, right? And 38 times 3 plus 5. We found a pattern. We found a pattern. That's very promising. 119 times 3 plus 5. And for good measure, 362 times 3 plus 5. It's satisfying to see that. Okay, so we found some sort of closed form for at least the n equals 2 case. We still need to generalize. Um, okay, if this is 3 times the previous, yada yada, it is 3 to the something that is growing. 3 times the previous minus 5, right? So what if we just take this whole thing? If we multiply that by 3, okay, so we can move this 3 inside, right? So this becomes 3 times that expression minus 3 times 16 plus 5, right? And this 3 can be subsumed into here, plus 3 plus 1. So we add 1 there, right? Um, yeah, so that's just the n bit happening. Okay, this line looks a lot like the next line now. So 3 times 16 plus 5. Um, great. So this is just going to be minus that whole expression times 3. I think we have to do the same kind of math again until I actually see the pattern because I'm not seeing it right off the bat. So let's take this and we'll multiply that by 3 and add 5 plus 5, 3 times whatever. Okay, so we get here, this 1 becomes a 2, and 3, there's another 3 in here. There's a 5 times 3, and there's a plus 5. No, we missed something. Oh, wait, this is times 3 right there. Okay. Now, this reminds me of something we were seeing earlier, where we can extract here. Like if we can keep it at one end if we have the multiplication in there, right? So I think I want to move a constant into parentheses alongside the n. Um, that way, the part that's giving us the 3 it's 3 to some power, isn't it? Um, and remove this intermediate line. Is there some way to get this into there? No. Okay, just for a reminder, I'm going to step back a bit and I'm going to look at how at the closed forms for this in the case of R8 equals 1 and 2. So when R8 equals 1, this could be 2n plus 3, right? So 2 expands to that 1, 3, 6 minus 3. That became 2n plus 3. And then for R8 equals 2, then this became... Oh, and I had tried to write this in terms of R8, and that was my original mistake from earlier. So R8, 1 plus R8, R8 plus 1. Right, and that turned out to be a mistake when I was writing up 3. I shouldn't have deleted it. Do I still have it somewhere? Nah. So this is going to be 2 times R8 is 2. So 2n plus 2 times 4. So that's plus 5. Right. That looked like 2n plus 5, and that looked like 2n plus 3. Is that really what it looks like? No, 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 because it's 3n. Right, it's 3n. Was it 3n? Was that the closed form? To comment this out for a sec. So R8 equals 2. This is going to be 4, so 8 minus 3. I think we need to print that out again. We'll print out that line. So for the 2 case, let's print out that line. Yeah, it is 3n. It is 3n plus 5. Right. Okay, so when you're looking at this naively, the reason I bring this up is that when you're looking at this naively, you're thinking, oh, there's a factor of R8 in here, and there's a factor of R8 in here, right? But you can write it down much nicer in this way, and I think something similar is happening down here. where the factor can just be in one spot. So instead of 2n plus 3, we have, well, right, like the other general expression we could have written for this was R8 plus 1 times n plus R8. And I just want to get the R8 down to one spot, but maybe that's not necessary for the next line, right? So this is R8 times 2. Or times n. No, times 2 plus 1. Okay. That gives us the 3 and the 5 for the case where R8 is equal to 1 or 2. And the parallel here between this case and the next case is what I'm looking for. So we multiply by n. And the next case, we're going n to the something. N shouldn't appear on the right-hand side on this part. But ultimately, it's 2 times, and then that becomes 3 times. So this part here is like the part that's in the base of the power. It was 2 to the something, and it becomes 3 to the something. Well, no. When you expand it, it becomes 3 to the something, or 3 times something. But the 2 stays there regardless. So maybe then, there's some way in which... Okay, I'm seeing something. So even though this is 2 times whatever, and the closed form, the line is 2n, and then the line becomes 3n, 4n, whatever, right? It might be better to express it in such a way that it's always 2. So we might, even though we're seeing this 3 here, we might want to express that in terms of 2. So let's see what that looks like, and maybe that'll give us something nice. We can draw out that pattern. So this is, what do I have here? This was these are our successful cases so far. 1, 2, 3. Um, 0. Right, those are just our powers of 3 that we were building off of. So these 3, can we express those? Starting with this first one. Let's say it's not R8 plus something here, and it is just 2. Well, we still need to multiply by another 2. So times... And the number of 2's will depend on R8. So math.pal, and we could put R8 in here. So R8, 2 to the 1 case, is going to give us 1 too many. So this would have to be like a -1 at least. Okay, well, I mean, that's at 11 right now. But can we wrap this in? Wait, that 2 int. Oh, wait. 2 to the R8 minus 1. R8 in this case was 2 to the first power, right? So that's just times 2. Um, what gives here? This is going to be 8, and times 2 gets to 16. Oh, right. We're wanting 3 to the something. Not one more time. Oh, yeah, ignore that thought. Scrap that thought there. Um, yeah, so how do we get this R8 out of here? It's 3 cubed. Maybe I'm fine with it being in this closed form, in this inside as the base. Okay, if each thing is multiply the previous one and then by 5, let's just write that as an expression in terms of some n. So let's pull out the whiteboard and let's do some algebra. Okay, so um, do we know what we want to do here? So we had here, let's just write the full out cases. So here we had 3 to the third. Is that right? R8 equals 2. So this is 3 to the third minus 1. And then 3 to the fourth minus 16. So 3 to the third minus 16. So let's get an arbitrary term n, or let's say n0. So n0 is going to be this expression we got here, right? So it was r plus 1 to the n plus 3. And there's a minus 16 there. And in general, we have that n equals this expression. So n0 or n minus 1 times 3 plus 5. So 3 times that, 3n minus 1 plus 5. And if we can expand, if we can expand 3n minus 1, what is 3n minus 1? I guess we could solve for 3. What do we solve here to discover the recurrence relation? Well, we have a recurrence relation. I just want to write that in terms of r instead of being in terms of n minus 1. We welcome nerdery in here. So, right, if I can get n not in terms of n minus 1, I don't know why I chose n for both of those. Um, uh, that could have been a or something. These two n's are distinct. No, I should erase that. I should erase that. We want to write this all clear anyway. So we'll call it a. So a0. Let's write down a few equations. There's going to be r plus 1, r plus 1 to the n plus 3. So n equals 0 in this case, 0 plus 3 minus 16, right? And a1 equals um, r plus 1. Again, I think r plus 1 is not going to change. Wait, r needs to matter more. R needs to be in something else here. Does it need to matter more? I guess it doesn't need to be matter more. We want it to be in one spot, actually. For the r equals 0 case, actually, does this expression here even work in if we dropped it to 0 case? So, or r equals 1 case. Here we had 2n plus 3, right? Our general thing is 2 to the n plus 3. And now we have 3 to the n plus 3 minus something crazier. And we should not forget this. There should be a constraint on whatever we get here, because we're trying to get a general function for all r. Um, and I suppose starting on r equals 2 is making some sort of progress here. We at least have a closed form for r equals. Well, we don't even have a closed form for r equals 2. Let's just do that, and then we'll reconcile that with the closed form for r equals 1. So a1 is always going to be r plus 1 again. What happens when you multiply that out? It's plus 5 times 6. Yeah. So the previous one times 3. R plus 1 to the 0 plus 1 plus r. So 0. Oh, no. It's not 0. It's going to be to the 1 plus 3. 1 plus 3. Minus 3 and plus 5. Plus 5. You know what? This base case here, this case is missing a plus 5. Let's kind of figure out where that plus 5 comes from. So plus 5. That makes this, this needs to be 5 smaller, minus 21. And 21 is 3 times 7. 3 times yeah. Uh, some cube thing is happening to the right-hand side too. Or to the constant. Um, and we were trying to squish that into here. Geez, we had times 3 plus 5. Anyone seeing something here? Our the number 3 is going on this part too. This is a 3. Maybe we squash that back into there. Oh yeah, squashing it back into there is basically doing this 3 times the previous one. I just don't want it to be recursive. It can't be recursive. Because we're trying not to do recursion, right? The recursion here is obvious. Let's take this expression in particular, and let's just squeeze it in. So let's take out a 3. This becomes plus 2. Right, 3 times that. Oh, and this needs to be diminished. This needs to go back to 0. Or not quite, not quite. Let's try it again. Okay, so we're taking out a factor of 3 from both of these, or from all of these. So 3 times that, we can take a 3 out of that term, take a 3 out of that term, and we take a 3 out of this term by subtracting by 1. Yeah. I realize that's back to where we were earlier, but I'm thinking like maybe we expanded it in the wrong way. Because there's obviously like some sort of power thing happening here too. Um, you know what? You know what will help us here? There's probably a similar pattern in the 2 case where we could get a form that was like this, or in the 1 case, r equals 1 case, where we can get a form like this, where everything's a factor of the previous one. And if we compare that to its closed form, so if we compare the recurrence relation form to the closed form, then maybe we can figure out how to get the closed form from this recurrence relation. Yeah? That seems like a decent plan. Okay, let's do that. So in the 2n case, let's go back to this act.scala. And what we want to print then, well, we have these numbers here already. So 5, right. In this case, it's times 2 plus 3, times 2 plus 3. 2 times the previous one plus 3. Okay. So that means this, uh, write that out. Um, and there's the n minus 1 case. How do we mark that? Let's call it np. So 2 times the previous one plus 3, right? And how does this give us that? Mm, This is definitely something a proper mathematician would look at this and be like, yeah, I can totally do that. But I'm no proper mathematician. But you see what we're getting at, right? I think we at least all understand the problem. And if someone knows how to get there, you're allowed to nudge me, shove me if you want. It's already 1:30. This looks kind of familiar to something we'd written earlier. Here, remember when we wrote 2n plus 3? R1 equals 2n plus 3? It's kind of reminding me of that because we're looking at 2 times the previous n plus 3. That feels too much like a coincidence. Oh yeah. You still need to finish the self-test. Ooh, I'm glad to see people doing it. I do have ideas for what I could keep on working after I solve the actual puzzles. I'm intending to keep R8 symbolic here. You mean when you did your math? So you did this as maths, you know? Curious, Dave, did your approach just involve like optimizing with caches, smart memoization? I think the way I tried to memo was a little bit too naive. Yeah. Um, this runs great for the R equals 1 case. But okay, we're on the cusp of this, right? It feels like we're on the cusp of this. Um, so it's the previous one plus 5. We could just start snowballing some functions here. What were the differences between this? and this. So 2 times that minus 3. Like how, so in both cases, I got this from observation, right? I didn't derive one from the other. But in this case, like how would I have derived that? Maybe, so we have n equals that. So like maybe if we solve for NP, we have an A0 case. So like A1 equals 3A0 plus 5. Oh my god. Uh, building up from base cases, like you seems to have been doing it, I think. Yeah, you just approached as a recurrence relation. Cool, cool. Cool. Well, I'm on my way. I'm on my way. Nope, that's not useful here. Well, given that we have... Okay, let's just look at 2 concrete cases. Let's look at 2 concrete cases and see if we can... All right, so this is what this looks like when you multiply it by 3 and divide by 5, and then add 5. So I could actually just look up the Wikipedia page on recurrence relations and see how this is done. But I feel like this should work. I vaguely remember doing stuff like this, and I don't know, you do some source substitution. Recurrence relation. Okay. So, closed form. Okay. One can express in linear recurrences, the nth term is equated to a linear function of the k previous terms. Okay. This is a linear recurrence. When the order k is 2 and the linear function merely adds, like if we look at how Fibonacci is derived, the closed form for Fibonacci is derived, then we can just apply that same method to get the closed form for this. This example uses a linear recurrence with constant coefficients. Because the coefficients of the linear function 1 and 1 are constant constants that do not depend on n. Yeah, in this case, the coefficients of our function, well, it's 3. For these recurrences, one can express the general term of sequences as a closed form expression. As well, linear recurrences with polynomial coefficients, depending on n, are also important. Because many common elementary functions and special functions have a Taylor series whose coefficient satisfies such a recurrence relation. With polynomial coefficients, depending on n, are... solving a recurrence relation means obtaining a closed form solution, a non-recursive function of n. The concept of a recurrence relation can be extended to multidimensional arrays, that is, index families. Okay. Let's look at the page on closed forms. Recurrence. Nope. Okay, let's look up deriving closed form of Fibonacci. All right. Let's try these two. Oh, patterns you see. Act 221. I'm not quite seeing that pattern you're seeing, Bob. Could you explain? I'm not just seeing off the bat. Those desks are pretty abstract. I think a better non-spoiler hint, but maybe substitution. Yeah, I've said the word substitution a handful of times. I just don't know where to substitute it. So let's look at an example of someone doing a substitution on Fibonacci to derive it. So I know I've seen it before. I've seen substitution used to derive. Um, Hold up. Benet's formula. Well, there's that. Okay. Bxn minus 1 and Cxn minus 2. Proof of what? Such a sequence is uniquely determined by its initial values. Sure. We don't need a proof of that. One takes further to find the unique sleep. Okay, yep. We shall now apply all this to the Fibonacci equation. Okay. It follows that the closed form of the Fibonacci sequence must be of the form, since the roots of that equation. Oh, okay, roots of that equation. Um, X squared equals x plus 1? Why is that a... Use auxiliary polynomial. Auxiliary polynomial. Okay, this proof is a little bit uh, too high level. I want something that derives it with some a little bit more step by step. Um, okay, we have two cases here. We want a general case. Um, so for substitution to work, we want to express it all in terms of, we want an expression that's in terms of just r for one of these values, right? Yeah, exactly. So we want something that's in terms of just r. So if we substitute one into the other, if one is already in terms of r and we substitute it into the other, well, I mean, that's kind of what we have here. So like 3, Okay, so if an equals 3, an minus 1 plus 5, and we have concrete values for an an and an minus 1, right? So let's condense these. And then maybe we can pull the constants back out later. So in both cases there, they are R8 plus 1. Here's an n. The n I'm going to leave uncondensed. These factors, well, we want an expressed in terms of just r. We have an a0, we have an a1. We have two things. We have doing it with the base case probably makes the most sense. Minus 16, and this is that previous one plus 5. If you want, let's get a1 just in terms of r. Well, I mean, it is just in terms of r right now, in terms of r and n, but we want to have the same constants. Right, we could factor out these constants here out of this. Can we factor it out in some way? What kind of shape is a closed form going to have? Okay, when you look at the n equals 2 case from before, we had these two expressions. You know what? I'm just going to do a power. I'm going to do a power thing on the right hand side here. So minus, what is this going to be? We're just going to do like the expanded form, and then we'll get the nice form. So this is math.power of 3 times 16. Hold on. So here is something to the fifth, right? Let's do something. Let's pull this 3 out. Minus. This whole pattern, if you just keep writing out this pattern, so you've got 3. What are the last few values? Yeah. Let's write it out all the way to 5. Plus, yeah, we're always adding a 3. Times 3 times 3 plus 5. 362. Is that what we wanted? 362, yeah. Okay, and we are always just adding a 3. 3 times whatever, uh, times 3 times 3 plus 5, and we have to increment this here. Okay, 1076. No, we're missing something. Multiplied everything by 3, and then we added 5, right? There's a 5. Is there a 5 hidden here? This is 3 times 7 plus 5. Oh, hold on. I want to bring this 3 times 7 back up into here. I think. Because that is minus 3 times 7 plus 5. Right. Let's take this base case and let's expand that instead and see what we get. Because you're going to multiply by 3 and times 5. And now there's a 3 on both sides of this. Cool. This is actually might be progress. Let me catch up on chat. Maybe I'm behind you. Did I already get that 2n case? Yes, I got the 2n case. So the 2n is this right here. And that's generalized to any R8. My thought was to express things as f, x, y, and identify some special, more computable cases to build up from. Did that the hard way. How did I do this? I basically just did it for R8 equals 2. Yeah, I basically got these two expressions. And then I said, oh, they're kind of similar. They looked similar enough. Or no, you know what? I looked at the line. I looked at the line this made, and I was able to compute a direct expression for R8 equals 2. But I haven't yet computed a direct expression when R8 equals 3. But we're going to take this 3 here. I like having that 3. So we multiply this by 3, and then we add 5. So times 3, um, wait, times 3, 5 times 3, and then plus 5, right? And let's put the 7 at the front. 7 times 3. Okay, like that's the pattern. Let's go with that. So we add 3s. 1, 2, 3, 4, 5. And then this becomes a 3 to the something for each of these cases. Where 3 is basically just this R8 plus 1, right? So this is 3 to the 0th, 3 to 1. That's the first power. 2, 3, 4, 5. 3 to n plus 1, basically. Okay, let's do that times math.pow 3. You know what? I need syntax. Give me a second. Extension and int def star star and int equals math.pow n to the m dot to int. There we go. I don't want to keep writing math.pow. So this 7 times 3 to the, well, 3 squared, right? Yeah, cool. And then now we have a growing pattern, 3, third, fourth, fifth, sixth. Now the problem here is this tail of 5s keeps growing. So this becomes like the previous row times 3, and then times 3 plus 5. Right, so times 3, and we're just gonna get the previous one. Um, times 3, 5 times 3 plus 5. And that we want to squish down. I this is painful. Well, it's not really painful. It's kind of it is laborious. But sometimes staring at numbers for a long while is what you need to notice the pattern. We could reframe it. It's not painful, it's cathartic. Oh, yes. 506. Was 506 the next one? No, we want 1091. 1091. Okay. And the final case. I don't feel like we need that. Okay. Okay, you know what? I'm seeing, I think I feel at least a pattern, right? Where we can do substitution. We can do something like an, or let's say p, I don't know, an and then a n minus 1. I need a whiteboard for that. But we could subtract one from the other. And what do we like? Maybe let's do something like that. Let's line these up. And let's put myself behind here in case we can't see. Okay. So we have that. We'll just call this A and then B. So B equals A times 3 plus 5, right? So let's do like B minus A and sub that into there. So B minus A is going to equal, well, these terms all cancel out. So we have 5 times 3 times 3 times 3. And then we have this thing. So I guess we have two terms like this then. So minus this first one, as per usual. And then plus the one that we're subtracting. This is feeling like roughly right, like the right thing, right? And we can take this 3 out into there. and keep working with that. And we have this whole thing. Jeez. Let's let that run. Okay, I'm gonna replace this. We have R8 plus 1 to the 2 plus 3. And all that changes in the next row is 3 plus 3. Okay, that's a little bit easier to read. Can I see? It is painful and rewarding. Agreed. I'm glad you enjoy watching the squirm. Your approach to solving this puzzle sans spoilers? Then when I solved this, did you flat out memorize or did you? Oh, you're asking the approach. You transliterated the assembly to Python. Simplify the function until I didn't look so irregular. And those free side effects, memorize, rewrite in Rust. Yeah, my naive memorization led me to give up and look at math and hope that's a thing. And it's seeming promising, right? It still seems promising. So this n gives a plus 1 up here, right? Let's continue writing this out. So we have this term here plus that minus that. Okay. And can we simplify this any further? So we've got two similar looking things here. 3 to the third, 3 to the third. We can pull. Does it make sense to pull the 3 out? Let me rewrite this to the right of that other one. Okay, 3 times yada yada. Wait, hold up. No, let's just pull out the 7 part. 7, 3, 3, and this is 1 minus 3. Is that all right? I know it seems silly that I'm um, messing around with constants here, but I want to keep that in because like the constants might have. I don't know that the constants aren't affected by R8, or I don't know, or by N or something. I don't want to. I don't want to collapse it all the way just yet. But like if we subtract any 2, the number of 3's here is going to depend on, yeah. What we want to simplify out for sure is the R8's. Let's get the R8's out of there. So this is R8 plus 1 that many times, or 2. So we can reduce this to 2 and then multiplied by R8 plus 1, right? And then now we've got this factor in here, so it's R8 plus 1. We can pull, like this whole thing, we can pull out of both. And we've got R8 plus 1 minus 1. Okay. Is this getting us anywhere? So let's look, substitute in this B. A times 3 plus 5. Okay, so we can pull out the A by doing so that just comes 3 plus 5 minus 1. Oh, hold up. The 5 doesn't get pulled out along with everything else. 5 is a separate term. So let's move that 5 over here. And then we can pull out the A out of this. 1 times 3, 1. There we go. So this becomes 3 minus 1. Ooh, is 3 minus 1 something we're going to be able to divide? So let's move this 5 over. So we have minus 5 there. Oh. This feels really close. So, oh wait, 3 minus 1. Can we just divide all that by 2? There aren't really factors of 2 in there. And I feel like somewhere along the way, we lost things we really needed. R8 plus 1. We still have R8 plus 1 to the something. Times this. That does look like progress. Let me just collapse that all. This 3 minus 1, I'm kind of afraid to collapse that. I mean, we know some of these terms aren't divisible by 2. Here actually is a negative 2. Wait, where did the 1 minus 3 come from? Yeah, there's a negative 2. The 3 plus 1 is a little bit weird. Looking at these two, I suppose we could have done this with a smaller equation, right? Eh, This 5 to the third. This is basically, I know, 5 times 3 to the n, where n equals 3. I think it's worth saying that. Um, oh no, that's 3 to the 2. So it's 3 to the, I guess 3 minus 1. Or, hmm, right, and this term becomes 0 in the base case. No, it becomes a -1 in the base case. I don't like that. Right, this case is n equals 3. In the n equals 0 case. I should have just done this with the first two instead of trying those two here. Right, like, let's just do that real quick. Can we get something similar? First, let's write this all out in terms of my syntax. Just so I have to do all that 2int everywhere. That's easier to read. To that power. Okay, where these here are the constants. So it's still the right value. We have something that doesn't compile. That's this here. None of these lines compile. Okay. Looking at just these two here. There's a 5 times 3. 7 times 3 squared. What if we divided one by the other? Oh, well, actually, hold on. A equals, let's say if this is equal to A, well, B equals that, then A is equal to 3 times B plus 5. Wait. 3 times 11 is 33 plus 5. Oh, no, 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 hold up. A is that one, so B. Should I just rename those backwards? No, we'll do it this way. Okay. Okay, if I substitute this expression for 5, yeah, I'd like to make a write-up of some sort. I I think I'd like to make a video summary, actually, of the Synacor challenge. But I have a lot to go through for that. There you go. Okay, if we do the same kind of thing, A minus B, or B minus A again. Remove some of those factors. So B minus A, and we substitute one of those into the other, right? Well, we're always going to get B minus A equals, let's put B on top here. Okay. That's a little bit easier to read that way. This minus this is going to be R8 plus 1. So to the fourth and to the third. R8 plus 1 in the middle. I don't want to divide those. You don't want to subtract them. But I don't know. Let's write it out. So minus this. Let's just write the whole expression here. So we have plus 7 times 3 plus 7 times 3, and then we have a minus 5. Minus 5. Okay. So that still holds true. Cool. Let's simplify it a little bit. This 7, we pull that 7 out. 3 squared plus 1. No, minus 7. Plus 3, actually. Wait, what did I miss here? 7 times 3 squared, right? Plus 7 times 3. Oh, the negative is up. Well, right, it's the negative. So there's a -1 on that. We'll just make this a plus with a negative there. Yeah, there we go. And then the thing is, I don't know, we substitute this right side with A in there, or B in there. We're still going to end up with the same problem, which is that, so that's going to equal to whatever the right-hand side is, right? We pull out the A. So we have A times 3 minus 1 plus 5. That still needs to be divisible by 2. And this is 3 to some power minus 3 to some other power to a lower power. And I suppose that has to be I'll have to check out that write-up too. After this, of course. I mean, what is our A value? Our A value is 11. I know. Let's take this. Let's take this. We're going to keep working with this here. Maybe we'll find closed form this way. So let's do minus 5 on the other side. Minus 5. So this becomes 5 times 2. A in terms of R8. Why don't we just start collapsing some constants? Maybe we should do that. I mostly want to figure out what's happening with the R8 here. So if we could pull this R8 out, how do you pull this R8 out? It's something like an x, like x cubed minus an x squared. Can we solve for that equation? Can we factor the whole thing? I'm gonna collapse some constants and see if that doesn't give me something to work with. So to the fourth, we got 2 to the third. And like whatever the fuck's going on here. Negative 32. Let's just say minus 32 here. All right, minus 32. And, we divide all that by 3 minus 1. So we divide that all by 2. 2 to the fourth, divide by 2. Divide by 2, divide by 2. The thing is, are these partial expressions even? I mean, I assume 81 and 27. So neither of them are like really divisible by 2. So let's take their sum divided by 2. And this is a minus 16 at the end. Minus 16. Okay, and how do we move a divide by 2 out? We want to have sort of the same power. How do you move actually a divide by 2 inside of these? We need to know, well, Move it into the power. I feel like it's not good to be working with things that are not integral. U to the n plus 3 was the base case. Here we had 2n plus 3, and here we had 3n plus 5. And that generalized to 2n plus r8 plus 2 minus 3. So that plus 5 that formerly had the r8 in it. Well, the thing is, this doesn't have the r8 in it. It's just, it is a factor of, yeah, it doesn't have the r8 in it, right? So what's, it's still not constant, is the point. What more can we do with this expression here? What if we divide both sides, or like we multiply the top and bottom? So that whole thing, let's say, divide by r8 plus 1. And for that to work, we have to multiply the insides each by r8 plus 1, basically incrementing this. No, that's not the approach we want. Well, if you multiply the whole thing by r8 plus 1, that might actually just be backtracking. Then we could subtract. This becomes 3, and that becomes 2. Still 54. Mm. Yeah, like if we did this enough times, so let's make this squared. We keep subtracting from the other two, right? So not squared, but third. Then we could subtract 2 from this. That's to the 0th now. And it's to the first, right? Oh, did I not do that right? Minus 2 times. So this is to the first power, second, third. Let's just do it one at a time. So we'll square that. This drops to 1. This drops to 2. So that should also be 54. Interesting. Let me just write it out like this. I think we have some paren order issues. Okay, I think we need to put parens here. Squared. 54. Hmm. So if this was 3, this one would be 0, which means this whole thing is just 1 minus 1, and this becomes 1, right? So that just becomes that. So this whole thing then becomes R8 minus 1 plus 1. This whole thing just becomes R8 times R8 plus 1 cubed. Am I doing that right? I'm not sure if I'm liking this, but we could see what it looks like. Okay, so we substitute that back into this expression, right? So that takes this whole thing that's being divided by 2. I don't like that we have 2 R8s now. But like I do still like that that is simpler. R8 times R8 plus 1 cubed. Why don't we expand the cubed a bit? So what would this be? R8 cubed plus 3 times R8 squared. I think we need parens there. Plus 3 times R8 plus 1, right? Mm, no. 1331, right? If we're R8 plus 1. Oh, hold up, hold up. So there's the R8 cubed. There are 3 ways to get 2 R8s. We'll do it the slow way. So we have basically that times R8 plus 1, right? Oh, what happened here? R8 plus 1 squared times another R8. What's R8 plus 1? Oh, wait, no, the whole thing is times by R8, right, on the outside. Mhm. Yeah. And then this thing expands to R8 plus 2 R8, or R8 squared plus 2 R8, R8 squared plus 2 times R8 plus 1, right? Yeah, and then it should expand to, let's just try it. So I'll just make 2 copies of this. We'll do this a really slow way, but I think I'm missing something. So R8 cubed, 2R8 squared plus R8. And then to that we add, right, times R8 plus 1. So we add plus the R1 bit plus itself. Yeah. And we collapse that into there. So we get now 3 of these, 1, 3, 3, 1. It's just like Fibonacci binomial. Okay, 2R8 plus this, so 3 times R8 and plus 1. So what is the difference? What? What is the difference between these two lines? Does anyone see the difference between these two lines here? Oops. One is apparently 54 and the other is 46. Is it a stray paren? An off constant? I don't know. I don't know why that's 46. Okay. But now it's a whole thing times R8. So this becomes R8 to the 4th. R8 cubed. 3 times R8 squared. And R8. Okay, so we've got this for A. But somewhere along the line, we lost the N. Right, so how is this in terms of N? And like, what would the B look like? The B is the bigger number. So the A case is B equals 1, is N equals 1, right? Yeah. So that's when N equals 1. And we basically just need a variant of this. We subtract some 1s to 0s and get 11, right? And if we get that, then we found it. We found the function. So R8 to the 4th. What is it that makes this scale? Well, you have to have 3 times R8 to the 3rd. Oh, wait. This 3 times R8 to the 3rd can be collapsed. So let's take a look at that. Let's keep going. Um, 3 times, so that becomes 4. Oh, wait, what? Oh, no, we're making assumptions here. RA is 2. My bad. I don't think it's a 1331 part. Let's just look at 3 of those terms here. Wait, A equals 11. A is our smaller one. Oh, 8 doesn't equal this. What was I actually simplifying? Right, is that divided by 2 minus 16? Okay, so we simplified that thing a bunch. Divided by 2 minus 16. And when we wrote this, we were just expanding the cube part of the inside, right? Yeah, so we were just expanding the cube part of the inside. And the actual expression then becomes, this is the thing that's being divided by 2. Is the 2 like coincidental because we are R2? Oh wait, we know R8 is 2. Uh, we're not trying to solve for general R8 right now. Fuck, yes, we're just trying to solve a general, we can just cancel out the R8s. We don't need the R8s in there until we're generalizing to all registers. We're just doing this for the case where it equals 2, and what we're generalizing over is the N, not the R8. So this is safe to divide. It was safe to divide even earlier. But I did expand it, so let's take a look at the expansion and see if, this is a thing we can work with. So that should be true. Okay. So when we divide by 2, this becomes 3. This becomes 2. This becomes 1. And this becomes 1. Now we can remove that div by 2. All right, but we can also keep the expression from before we tried to do expand that cube. Where is that? Here, 2 to the 4th. Let's compare it with that. Divide by 2. When we divide that by 2, we just basically drop that to squared, and we drop this to cubed. No, we don't, because they're the plus ones. We couldn't actually do it there at that point. Right. So then doing that was a helpful call because it allowed us to do the div by 2. Cool. We don't have to divide anymore. Okay. Well, let's pull this out here. Or, we'll make a new line. And this becomes just plus 15. R8 to the 1 is just 3 times R8. So that's, 6. That's a constant. But we need to be doing this in terms of 1, of n. Where was n this whole time? N was in the exponent. Okay. Yeah, n is in the exponent. Um, okay. Unfortunately, this is like n equals 0. What if, just to take a step back, when we did this for Ra equals 2 with n equals 2, what we did was just look at this and make up an expression. Can we look at this and make up an expression for all of that, knowing that has something to do with the power of 3? Let's take a quick detour, reset our brains a little bit. And I'm going to do just that. So we have some values here. We see some things we're doing. I don't know. We have plus all these constants. Let's take, and we know that for the base case here, we had 2 to the n plus 3 minus 3. So we should collapse to something similarly simple. What if we looked at the base case for r equals 3? For yeah, what if we looked at the base case for r equals 3? And then try to get the general case that way. There's another thought. Can we keep the constant constant? Or at least not like expanding in power. Um, if we have a polynomial who's always so we have some n. What's the highest degree of this polynomial? It's going to be 2 to some thing, right? And that's going to grow. The case with the 2's, this was 2 to the n plus 3. This is not a polynomial, so I shouldn't be thinking about it that way. Man, how did they even find the original closed form? Like, how is that derived? Okay, let's go back here. We want to compute Acc opt. I think we just acc. For 3, 0. Acc 3, 0, where R8 is not 1, not 2, but 3. So acc 3, 0, 3. The very first element of this. And can we get an expression for that? Um, 19. Okay. So whatever next iteration is, we've got. So this was 11. This here, where we have 0 plus 3. And where did the R? 2 plus 1. So like this is the R8 bit. R8, R8, R8 plus 1. So that was 5 and 11. And the next iteration is going to give us 19. So the next iteration is almost certainly going to be like an R8 plus 3. R8. Wait a second. This is R8 plus. This is R8 plus 1. This is the previous R8 plus 1. So this is 1 plus 1. This is 2 plus 1. And this is 3 plus 1. Where the growing number here is register. And we have to get 19. $64. 64 minus 19, 45. Okay, so we have minus 45. Okay, and what happens with successive values? Well, let's print some of those. We have 2 of these things here. Wait, which one did we want to keep? 2 to the n plus 3. No, we're not sure about this generalized version. And this closed form is only valid for I equals 2. So we just comment that line altogether, don't we? But at least we have this bit optimized, yeah? No, we need to leave that optimized so we can calculate things. Oh, you know what? This is the wrong value. This is the wrong value. For 303. Oh, right, no, we did ACK, not ACK opt. All right. 303. Let's try 313. And if we're feeling brave, let's try 323. If that doesn't work, we can swap it out for ACK opt and just comment out the optimization. 1983, 339. Okay. So this goes 1983, 339. And there's some like multiply by 4, right? So in this case, 19 times 4 plus 7. Okay. 83 times 4 plus 7. Okay, great. Well, that's for RA equals 2. We're seeing patterns all over the place. We just haven't found like the mega pattern. um, cool. So we had times 3 plus 5. Now we have times 4 plus 7. Um, minus 3, 16, and then minus 45. But this is times 3 plus 5 something. Oh, this is, yeah. And you know what? For that matter, what was it with just plain old Ackerman? So here's a case. Register is just 1. 5, 13, 9. Times 2 plus 3. Times 2 plus 3. Cool. Yeah, regular Ackerman was times 2 plus 3. I'll just write that out. 5, 13, 9. 5 times 2 plus 3 equals 13, and 13 times 2 plus 3 equals 29. I'm going to move this down where I noted that pattern here. Let's do something similar. So we have 11, 38, 119. Let's just do this times 3 plus 5. And now we know that the closed form for this one was, what was it? 2 to the n plus 3. 2 to the n plus 3 minus 3. And it was looking like, so R8 equals 1 here. The 1 could come, well, the 1 was certainly in here, 1 plus 1. So we could have 3, 2. It's not a constant subtraction at the end, though. But maybe there is a, maybe that's a factor of something. Let's look at these cases. What is 5 minus this? 5 minus 21. Oh, right, that's minus 5. Because it's always 5 times the last plus 3 times the last plus 5. Here we were inferring like that based on the fact that that's 16. me expand it to this. So here's our 11. 7 times 3 plus 5. We could kind of like go backwards and infer a negative case from here. Like, could you extend that to -1? Right, so we take out the plus 5, we take out the times 3, and then this becomes 2. If there was a -1, that value would be consistent with this. That's silly, but it's there. But what we'd had before was this. There was never a times 3 anything. I lost you like 3 hours ago. I think I lost myself at some point too. I need to find myself, and that's how we'll get out of here. Um, what is this function here? Is it possible? So if the constant here keeps growing, how much is it growing by? This right side. It's basically kind of growing in the same way. So we also have probably a constant that is 2n, right? So it could be 3 times n plus, wait, I think it's still going to be n plus 3. That's sort of what we started with, right? Where were we here? Yeah, we started with 3 to the third, and then we're adding a constant, or we're adding other terms. I don't think that's going to be a constant, but 3 to the third. So we could do the same thing here. 3 to the third. Then this is probably going to be something like 4 to the third. So how do we get the 19? The first term. So we were able to get the first term of this. Let's write that out explicitly. 2 to the third minus 16 was equal to 5, right? No, actually, not 2 to the third, but n plus 3. Oh, yeah, so that's 2 to the third, sure. Wait, the first value is actually 5. Nope, I meant to write that here lower. 3 to the third minus 16 is 11. Okay, is the first value. Here we have maybe it'll be fast soon. I feel like we're getting somewhere. We're getting somewhere. 2 to this is also 2 to the third, but it's minus 3 gives us 5, the first term. Okay. And in this case here, we've got 4 to the third minus something. Okay, we're trying to get 19. 64 minus 19, 45 minus 45. is the first term. Okay, so how do we generalize this across these three? In terms of R8. So the R8 obviously appears here. So it's like I don't know, R8 plus 1 to the third. But the right-hand side we need to do in terms of R8 2, and in terms of R8 scaling. And I think it's just scaling slower. So how can we get 16? We can have R8 to, I mean, this is R8 to the fourth. So like that gives us 11. But in this case, what does it actually become? So you've got 1 plus 1 minus 1 to the third. Not quite. It's 1 times 3. Hey, it's not going to be big int. We are U16. But have a good one. Nice to see you. Zuno, am I circling around something? Like, if I circle around this long enough, will I get there? Assuming you took, like, the same kind of approach here. You know what? 2 to the fourth is too much. 2 to the fourth is too much. Let's do, like, R8 plus 2 squared. So R8 plus 2 squared. Yeah, it's got to be a smaller power than this one here, which means for this one up here, we would do 1 plus 2 to the first power, right? Okay, cool. I like the parallelism there. Now let's try it for 4. Now here we would have 3 plus 1 to the third minus R8. No, in this case it's 3 plus 2. And is this going to be to the third? Damn, no. Okay, let's look at what it needs to be. So 3 plus 1 to the third. This was 3 to the third, right? So this is 2 plus 1 to the third. 3 plus 1 to the third, 64. That's over by how much? 45. And we need to get 45. That's not going to be a clean cube of anything. What's a cube root of 45? Yeah, no. But maybe there's another term that starts appearing. I don't want it to be like an infinite number, an infinite tail of terms as R8 increases. We need to have a constant number of terms. Yeah, maybe just having the 1 and 2 is enough, and I don't need to generalize 3 also. That's fair. I could try that. And maybe I should try that. This was lucky that it was to the 16th. I mean, it's not always gonna start as like the difference of a cube and a square or something like that, right? That's kind of silly to think. Oh, hold up, hold up. I'm scaling this incorrectly. Look at this here. Um, this first never actually changes. This first exponent. So we don't want to be scaling the second exponent, right? Like if this is squared, this should also be squared, whatever it is. So 1 plus 2 squared, nothing squared is going to be 3. Uh, well, it needs to be some linear function then. What goes from 3? Let's just look at that. We get 3 to 16 to 45. That looks like a parabolic function. So 3 to 16 to 45. Um, what's the gap between these? So for each of these deltas, we have 13 and we have 39. 39. Hey, that's 3 times that. Cool. This is looking quadratic. We might have found something. So, right, in just y equals n squared, we go up to 1, and then we go up to 4. Here we go up to 13. We go up by 13. Okay, 0, 1, 4. We go up by 1, and then we go up by 3 to 4. Here we go up by 13, we go up by 39. So, and then what's our constant then? So this is basically y equals 2. Okay, so there's x squared, but this is scaled by 13, so 13x squared. And then there's a constant. So this would be equivalent to like the 1 squared. No, 0 to 1 squared. So plus 3, right? And then for 0, um, when y equals 0, or when x equals 0, rather, then we have 3. And when x equals 1, we have 16. And when x equals 2, we have 13 times 4 plus 3. 52 plus 3. Wait, what? No. 13 plus 3 equals 16. Right? Am I not doing that right? 13 times 4 plus 3 equals 55. This is not 39, this is 29. Okay. 16 plus 39 equals 55. Well, maybe that's not quadratic. Uh, let's do this. Y equals ax squared plus bx plus c. Or and when we have y equals or x equals 0, that should be 13. So we'll do a system of equations here. So when x equals 0, 0 squared is 1, we have 13. B times 0 equals 13. So then we have a, b times 0, so a plus c equals 13. Okay, now let's put in 1. When x equals 1, we have 16. So x squared, that's just 1. Wait, yeah. 0 squared is 1, 1 squared is 1. Oh, wait, hold on. 0 squared was 0. Yeah. So c equals 13, right? So a plus b plus 13 equals 16. So that gives us that a plus b equals 3. Okay. And now let's do the third equation. Wait, is that enough? No, we have 3 unknowns, so we need 3 equations. Yeah. Equals 45. Okay, so quadratic formula, neg b plus or minus square root of 4ac all that over 2. That doesn't really help us find a. No. Let's not even think about that. So we do have that c is 13. So let's at least do that simplification. Plus 13. 45 minus 13 is going to be 33. 32. And we have a plus b equals 3. I don't want to just sub a and b both, though, because I want to solve one or the other. A plus b equals 3. let's just substitute b in there. Let's say b equals a minus 3. So given b equals 3 minus a, then this becomes 3 minus a 3 minus a times x. Let's just distribute that. So 3x minus ax equals 32. Um, Wait, we know what x is in this case. Sorry. Right. Let's backtrack just a sec here. Geez. Okay, you can tell I'm tired. I forgot what I was doing. So we had that when x equals 2, this is 45, right? This was when x equals 1, x equals 2. So, so this is much simpler. I was making it 2 squared. So 4a plus 2b plus c equals 45. We already know what c is. So that's 13. That equals 32. We can probably just divide across. So we have b and 2a equals 16. Okay, and since we had a plus b equals 3 earlier, so a plus b equals 3, and 2 times a plus b equals 16, we can just substitute one for the other in there. And a equals 3 minus b. No, I don't want to do it that way. I'll do b equals 3 minus a. Okay, so this one here becomes plus 3 minus a, which means 2a minus a is just a. So a plus 3 equals 16. A equals 13. And if a plus b equals 3, then b equals negative 10. B equals negative 10. Okay. So let's gather that with our c. And that's a 316.45. So a times 2 squared plus b a times x squared, where x is our number of registers. Okay. Okay, 13 times well, hold on. Where do we want to plug this? Oh, we lost this case. Push all the way down here. I'm gonna move all this below so that our code's together again. Yeah. That's a long little diversion. Okay, 13 times R8 to the second power minus 10 times R8 plus 13. Okay, And that's the constant we have here. So it's minus that, plus that, minus that. And all this stuff that doesn't actually compile, we gotta comment it out. We're done. That scratch that. I should open a different file for that. What do we have here? Let's comment that out. Okay. All right, in this case is 2. It's 2. Fuck, when I solve an equation, I'm supposed to use 1, 2, 3, not 0, 1, 2. No. Okay. We'll give it a little shot on the right. I did think that was worth it. This has now become a math stream. Great. So we know this 13 or 3 rather. So for the base case, -3. -3 equals a times 0 squared plus 0x plus c. And we have 13 equals a times 1 squared. No, that's not 0. That's the same mistake I made earlier. -3, this is 1. 1. And then when we have -16, so for this one, where did I put those 3 cases? Yeah, 16 and 45. -16 minus 45. This is when it's 2. And then minus 45 is when it's 3. 3 squared, 3x plus c. And we're doing this because it looks roughly quadratic. Although, we did try to fit something. We found 31655. Maybe this here is a dead end. But let's at least, okay, we'll simplify these. So this becomes 1. So a plus x plus, no, 1. Why did that become 1x? These are supposed to be b's. Plus b plus c. Okay, b, b. So here's 4a, and here's 9a plus 3b plus c equals that. Okay, So is there a solution here? Does this fit a quadratic curve? A plus b plus c equals -3. Well, let's solve away and plug. So let's solve one for c. C equals -3 minus a minus b, right? And we can plug that into here. Okay. And we can simplify this a bit. Plug and chug away. So plus b, there's a minus b there, took that out. And then 3a. 3a plus b minus 3 equals 16. Let's move this -3, so equals -13, I guess. Okay, and then we can solve that for b and plug it into this third equation. So this is b equals -3a minus 13. So let's take that, and that whole thing's getting multiplied by 3. Okay, and now we can solve for a. So this is a 9 right off the bat. We have 9a. Minus 9a, minus 9a. Hold up. We still have a c in here. Okay, well, minus 9a minus 39. Minus 9a minus 39. 39 plus c. So the a's cancel. And we add 39 on the other side, so this becomes -6. C equals -6. Okay. Well, if c is equal to -6, geez, okay, where do we plug this in next? Well, let's start with this. So c equals -6. So a plus b equals 3. All right. That's a bit more promising. And let's say, I know, I want copies of these. We already used the first. C is -6. So -6 on each of these. -6. So this becomes -39, -10. Okay. So I hope I'm not just scaling this in. That should be enough to find a and b, right? Let's take this expression. -4a divided by 2. Is this something we already got before? -2a minus 5. -5 minus 2a. Huh. That's a little bit sus. Remember getting b equals negative 3a minus 13? Because did we drop a c or something? Yeah. Okay, you know what? The math part. Did I make a mistake? No, we plugged c in. We got b equals negative 3a minus 13. That might, that might also be true. And negative 2a minus 5. That's a contradiction, right? Like that can't equal that, can it? So plus 3 to both sides, we have a, well, we'll make a copy. So a plus 5 to both sides equals negative 8. Which means b yeah, if a is negative 8, then this here is minus 24, plus 24 on both sides. 24 minus 13 is 11 equals b. Okay, we've got a, b, c values then. A, b equals 11, c equals negative 6. It's just black. Actually, no, it does still look green. Right, it's not, the glasses don't tint things as red as they look. But I guess, it is a little bit, and I found that greens in general kind of sometimes pop with these glasses. You suspect the comments are invisible? Oh, I've been missing a lot. Oh, like, oh, no, you mean uh, the worksheet comments. No, they pop out. They still pop out too much. Okay, so we have these three things here. And let's try to plug that in. Okay. Negative 8. Like 8 times R8 squared. R8 is 2, right? Yeah. Plus 11 times R8 minus 6. That should be the same value as this up here. Jesus. Not even close. Not even close. That felt like a longer digression than I intended. So let's take a step back. And why are we doing that? Um, we have an expression that gives us the base case when n equals 0 for register 8 values of 1, 2, and 3, right? So this 2 cubed plus minus 3 evolves to 3 cubed minus 16, evolves to 4 cubed minus 45. And I was trying to get an expression for all of those in terms of R8, right? Like if this is going to generalize at all, we could at least generalize the base case. So I was thinking instead of just trying to generalize R3 for all n, I'm just going to generalize um, over R for n equals 0. Um, I don't know. You know what? I don't mind outsourcing this part of the math because if I know what math needs to be done, I don't even know if Chat GPT could do this, but when uh, r equals 1, um, we have that. When r equals 2, we have 3 cubed minus 16. When r equals 3, we have 4 cubed minus 45. Is there a pattern here where we can compute this? Uh, let's call this B. B in terms of R. Oh no, the answer to what? Like your generalization? Okay. R squared plus 3R plus 1. Huh, look at that. Um, we'll, we'll let ChatGPT do the math of that part. So let's try this out. Um, I'm not exactly a mathematician anymore. R squared plus 3R minus 1. So we have, if this thing was a thing that we were subtracting, 2 cubed minus 1. Oh, hold up. No, that can't be right. There has to be a cubic factor in here. Maybe it's just that in the base case. Yeah, that's not working for me. Because I can't turn that into something of the form, right? Like this is a generalization here. Um, well, hold up. No, we don't want it to give me all of that. We just want it to give me this right-hand side. Because we kind of got, we're pretty sure that this left-hand bit, this 2 cubed, 3 cubed, 4 cubed is correct, right? And then now it's going to give me a linear function. Or, you know, it's not going to be able to, maybe it won't be able to fit anything to that. ChatGPT can on so it gave you the answer to case 3n. Do I F with lean? What do you mean F with lean? I started trying to, oh, like do I mess around with the lean programming language? No, I've never played with it. I've been holding off on on GPT for 3n, but I'm envisioning a way to symbolically unroll it with something like senpai. Wait, so Zuno, you don't have 3n? Are you just doing it with 2n? You're trying to do it with senpai right now because you want to earn it in some way. So Zuno, did you figure out the general for m equals 3? Or stop at m equals 2? Because maybe I should just move ahead with the 2 case generalize and not worry about 3. Let's see. 2 okay, we're going to delete this line here. And we're going to put a guard here. This only works if R8 is equal to 1. Yeah, that's fair. And we don't have the general case yet. We don't even have the 2 case, even though we are so close. We could at least give it a nicer recursion, right? So our general case, it's going to be the previous one. Yeah, we could, right? We could at least give it a nicer recursion. So if R8 equals 1, or if R8 equals 2, it's not closed form, but it's nicer recursion than the default. Then this is where the times 3 plus 5 comes in. So what was that? It's actually running code. Yeah, times 3 plus 5. And we can give it the base case. And maybe if you put in enough of these, R equals, then we get acc opt of 3n minus 1. Yeah. 3n minus 1 R8 times 3 plus 5, right? That's still totally valid. Like one Bob mentioned, even a few simplification at lower levels massively boosted performance. Yeah, that's true. We were already seeing that. But I think I could at least generalize this part because we had times 3 plus 5, and then the recursion, it became like times, so it's like times 2 plus 3, times 3 plus 5 times 4 plus 7. That was a pattern. Yeah. So let's get this out of the way here. And that much we can at least generalize. So for general R8, then actop 3 n minus 1 R8 and I guess once the right side hits 0, then we're good or something like that. So for r equals 2, for r equals 2, we are doing times 2. Or for r equals 1, we're doing times 2. So it's going to be times r8 plus 1 plus, so it's plus 3 plus 5 plus 7 plus 3 plus 5 plus 7. So that's 2r8 plus 1. 2r8 plus 1. 2r8 plus 1. Oh my god, this seems familiar. We were doing like a 2r8 plus 1 thing earlier somewhere. Two R8 plus 1. R8 plus 1. This is familiar. This is familiar. This is the 2 case. This is the 2 case. Times n. Holy shit. And this, the closed form we ended up wanting for this 2 case was this 2 times n plus r8 minus 3, right? So if you go from that to that, so let's take that, and let's say this here is the n, right? R8 plus 1 times n. We actually want 2 times 2 times n plus r8 plus 2 minus 3. That should also work. Okay. I think we have something we can work with. We just need to verify some correctness here. And of course, this case is not going to be reached. We have to choose one of them to comment. Are these equivalent? So if we multiply that plus r8 plus 2, 2r8 plus. I'm just going to multiply this again just to make sure these two expressions are actually the same. So we take that, we multiply each of the terms by 2. So that times 2, R8 times 2 plus 4 and minus 3. So plus 1. I don't know. I'm not confident enough. We're going to leave that commented. This is already getting us much of the value right here. Yeah, that's getting us much of the value. And let's copy paste this into our other sheet and do some. Oh, we're already here. We don't need to run on the GPU. This is blazing fast. We've optimized this. So let's do some comparisons. Let's do. Can we do 3, 2, 1? Ack opt 3, 2, 1. 3, 2, 1. Oh, okay. That was too easy. Let's make R8 equal to 3. R8 equal to 3. Oh, is big. We had not even hard-coded that case. So I expect that to Stack Overflow. Yeah. But 2, I think 2 we had computed. No, 1 we had computed, and we got the right thing. Yeah, it's gonna Stack Overflow. Geez, at 3, what can we even test? R8 values just. Okay, so we can't run it against our normal Ackerman, I guess. But, you know, we could at least see if we can get a value. So I don't know, let's try something like this. We'll just have it on auto run here. Unused, thank you for that. I'm just gonna remove that warning this way. Okay, so we got 29. Let's make R8 equal to 2. Huh. Why is the stack overflowing now where it didn't before? We were able to compute 4, 1 with R8 equals 2. So let's see if we can still do that. 4, 1 with R8 equals 2. Oh, interesting. Oh, hold up. In our recursive case here, we're not passing along R8. No, we are. We are passing along R8. So that's doing what it's supposed to do in that case. Had we actually computed with R8 equals 2? Yeah, we're just getting the same answer. Well, let's remove all the 3 cases. Stack Overflow. We need other optimizations. All right, we can do 4, 1 just fine if we add case 3. Oh yes, I will still want memo, absolutely. Yeah, let's add that back in. Val memo equals map.empty of a pair of ints to an int. And I think I should integrate the mod here too. Lazy val calc equals that. Oops. Memo.get or else update. I need to pass along m and otherwise it's calc. Yeah, it would just run away right away. I don't have like I could also just inline it into here. Or you know what I could do instead? I just make this an inline def. That's gonna be the most performant. Yeah, that way it's just a definition that inlines here. Okay. So for one, well, okay, we still have the issue of this being 412 65533, giving us the same answer even though R8 is equal to 2. What's the general case here? Accopt is not passing along R8. R8 needs to go there. R8. Right, because it defaults to 1 otherwise. Okay, now that's doing that. And we stack our overflow. Use local definition. We never use that. You know what? You're right. We shouldn't have that as a default. Mm. This is generalized to all R8 here. You don't want your functions to run unless you ask them to? Yeah, this doesn't run unless I ask it to. That's what a lazy val is. 411 should work fine. Yeah. Yeah. Oh, yeah. So this is strict. Well, this isn't a function, right? So this is a val, and I'm just making the val. It's like if you had let, or I don't know, how do you declare a variable in Bash? Um, but this here is a function. So val is just a value. It's like, val x equals 13 or something like that, right? And then def is the function. And it isn't strict val. Okay. Friggin' stack overflowing. Um, do I need Is it okay? Well, I know this. Uh, Act41 won't run. I know that Stack Overflows. But this should be able to run. This runs in a worksheet. So it should be able to run in the REPL. In JS, you did like let fn. Yeah. Well, I mean, I could do like you could do that here too. Like you just make that arguments if you want, and then if you just pass around calc, then that's a queried function, and that won't run unless you do that. So you're passing around, you're passing around the function value, or so in this case, I'm passing around the function value until I do that. But if there's no args on it, then it's just that. And I think getter else update, even that has it by name on the value. So it won't evaluate it unless it needs it. Okay. Yeah, lazy also memoizes, but I don't ever need it again. So an inline def probably makes the most sense here. Unused local function. Okay. What to do about these stack overflows? We do pass around an explicit stack size. Build.spt. I'm gonna have Copilot here. Just increase our stack size. Um, 8 megabytes is reasonable. Let's just do 60 megabytes. And maybe like something overwrites what I pass in the command line argument when opening up SBT. So I'm just gonna put it in here too. Well, I don't want ChatGPT to think I'm crazy. So I'm just saying megabytes here. I'm gonna change it to gigabytes when I get my hands in the code. All right, well, Copilot's taking a second to think about that. Okay. Added the Java options. Cool. Let's keep that. We'll reload SBT. Reload. And let's try again. All right. Is it possible to write in TCO form? I don't. It's not possible to make this tail recursive, or at least so like one of the calls is a nested recursive call, right? So you couldn't tail call optimize that. For the same reason you couldn't do this with a for loop, I think. I think I'm understanding that correctly now. All right, so the Ackerman function, it's not primitive recursive. And I mean, just looking at it, so what Scala can tail call optimize, I don't think anything could tail call optimize this. Like the one branch that's doable. Well, let's take a look. So this branch here, that's in tail call precision. But this one here, I don't think you could do that because it's required by the other recursion. Yeah. Yeah, exactly. Okay, so here we go. We've reloaded. Let's go to ACK. Let's try R8 equals 2. Whoops. R8 equals 2. And we are still getting stack overflows. Okay, I could rewrite this to put it on the heap and just have a stack. Yeah. Yeah. No, that's a stack overflow. Wait, am I getting an integer overflow error that's causing it to stack over? Yeah, it happens so quick. Exactly. That's what gets me. Am I getting an overflow into a negative number? Am I getting an overflow into a negative number? Oh my god. That's I think you're right. I think you're right. Assert m is greater than 0. Well, hold up. No, no, no. Because that should, yeah, it goes into an infinite loop because after m is greater than 0, then like, or less than 0, it just keeps doing this. It just keeps doing this case over and over again, right? Once they're both negative, and it won't hit any of these shortcut cases. Assert is m is greater than 0. Assert n is greater than 0. Um, wait, what? Assertion failed. Okay, yeah, assertion failed rather quickly. Shall we just use big int? Or when we return a thing, we, so here's the calc. We take this calc and we mod it. And 0x7fff. There we go. Yeah. That's an appropriate place to do it, right? I don't need to do that anywhere else. Cool. Hey, cool. We're running. Is that what was happening when I was getting it fine before? Oh, well, adding this mask fixed it anyway. Um, I think I could run with this. That's pretty fast, yeah? So we could look for a value R8 such that mod this mask at its equal to 6. So var R8 equals 1 or 0. Let's start with 1. I guess it could be 0, couldn't it? If R8 is 0, what happens here? Yeah, this is recursive with Ackerman 0. N minus 1 and 0. Yeah, totally. And var and equals 0, whatever. Well, and is not equal to 6. We're gonna do a thing. We're gonna do accopt R8. Um, let's increment R8 first. And once n equals 6, R8 is our value. R8 equals R8 gives ACK 41 equals 6, right? Oh, wait. And it's always going to be mod 7 FFF. I'm just going to do that mod for good measure. 0 x7 FFF. Okay, cool. Well, let's run that. You got it? You got your formula for case 3. Cool. I'll be excited to see that. I feel like I've done enough work on that I can be spoiled by someone else's solution to it. But let's make sure this runs first. I'm gonna use the bathroom. I'll be right back. Third order. Okay. It is still running. Am I modulating at the right times? Good question. Let's see what's even happening. Let's print each of these. So let's call it A. So A, A41 and R8. R8 equals ends. Like, should I modulate more? Oh, look at that. Look at that. The answer is not changing. And we've already looped through all. We need to have a limit on Yeah, you don't need to keep going. But because R8 itself has a max value. Yeah, it's a good, fair enough, fair enough. Okay, what is going on here? Wait, did I comment out all my 3n versions? I'd meant to leave this running here. I guess I don't even need it, do I? Huh. How about that? So just having this is enough? Oh, where did my 2 case go? My 2 case is missing. Oh, wait, no, 2 we hadn't solved. 2 is what we were working on. These here are 2, not 3. Let me verify that. Okay. So when n equals 2, oops. Uh, okay, m equals 2, then it is this thing. Where did my generalized for case 2 go? Here. I wanted this with me. Case 2, right. We have the case 2. Um, and the case 3. Here's like the recursive one for R8, and here's the general one, the general recursive one. But we don't need those, I don't think. We'll uncomment those if we need more juice. We're getting the same answer for everything because of the memo. Because of the memo needs R8 in there too. That's what's happening. Right, MNR8. Okay. It's doing plenty of searching. Let's uncomment this case here. See if it goes even faster. Oh, well, that stack overflows right away. Why does that make it stack overflow? Because it recurses a lot without the opportunity. We should probably memo, or perhaps every call, we should take our M and N. And already mask them. Or we should just use lits. I should just use my lit. I have all these things on lit. My case 2n is breaking it for you? Oh. Really? Oh. That's a shame. I guess I never tested enough in with bigger values. Okay, well, let's comment this out. Thanks for letting me know that. So let's do ACK 2, 0. Um, yeah, let's just do like 2, 4. And print line that. Okay, and let's say R8 equals 2. And we want to do the same for ACK opt. 1713. Let's run that again. 1111. Was this supposed to be -5 or something? Let's take this for various values of n. So 0 to 10, that map ACK to n, that makes string with a space. And you do the same kind of thing here, but just ACK opt. Oh, we can just have that be an underscore. Okay, so for 1, they're the same. For 2, they are off a little. So this should be, you know what? That's kind of what I thought I was seeing. This here, I don't believe. Okay, I think I had it somewhere. Certainly this one would work, right? That version. So R8 times n plus R8 times 2 plus 1. Okay, we'll try that. Okay, it's fixed again. We'll stick with this. I don't know how I ended up getting this version. Yeah, I didn't generalize that, or I didn't like change that properly. And just to make sure it's really fixed, let's do this for R8 equals 3. That means it definitely works for everything. Cool, cool, cool. Yeah. Okay, back to having things work then. So we'll comment that out. We'll go back to this run. Oh, and now we're stack overflowing. Let's remove this optimization. Okay, that's looking better. That's looking better, but could still be faster. And I'm also thinking I should just make these all lits. Make them all U15, stay in that space. Have some peace of mind. And what we could do is we could add an implicit conversion from int to lit so that we could write that in. So lit, 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 lit. Place int with lit. 1, 2, 3, 4. Implicit conversion from int to lit. Copilot toggle. No. Given conversion from int to lit. Okay, it doesn't actually know how I create my lits, so I think I have a I.2 lit. Okay, great. And that should fix everything else. What's going on here? Found a lit required an int. You require an int. Where do you require an int? Zero needs to be a lit here. But we can't do it that way, can we? Can we? Okay, so we'll have to make that guard. The 1 and 2 case makers faster. Great. Yeah, I believe it. I'm gonna use a lit here. Well, okay. Zero, 1, 2, 1, 1, 1, 2, 1. Okay. Oh, and there's no minus. So this here needs to be plus OX7FFF dot 2 lit. And then 1. And then this is a 1. Or another plus OX7FFF dot 2 lit. And then we don't need to do this mask here. Cool. And we just make all these dot 2 lit, dot 2 lit, alright, dot 2 lit. And we don't need to mask there. And found lit required int. I mean, I suppose this can be a lit then, right? 0.2 lit. And the answer that returns is always going to be a lit. We just make everything lits. Mm -hmm. Well, that ends equals 6. Two is not a member of lit, right? Lit and int can't be compared. That two lit. Cool. Cool. Unreachable case. Oh wait, we need to get the actual symbol here if we're gonna pass in a variable that way. All right, I think we figured that out. Now it's using lit, and what's the other thing we could do? We could try this 3 case, see if that general recursion works. This is too slow, still too slow. Yeah, for putting the symbol in. Yeah, I don't like it. Um, because it's not a why it seems to hang it. Maybe that's GC pauses. Or maybe it does struggle on particular numbers. Yeah, that is a logic too. Okay, well that's not going to be fast enough still. So let's have that take a break there. Um, let's try this. Let's pull out this thing. So mn if m equals 3.2 lit. I think writing it that way might be better. I really just wish I could put a lit 3 in here. And there is a way. There is a way. I can get like literals from my custom number type if I implement a case class or there's a class type for that. I was already 10% done. 31,000. Fair. Okay. Yeah, I could let that keep going. I could just start back off from 3128. Let's keep it going from 3128. R8 starts at 3128.2 lit. No, that's 1% there. That's not 10% there. Got it. Oh, and what happened now? Oh, what did I break? Is this because I turned everything into lits? Whoops. M if M equals 0.2 lit. 1, 2. And then this can be N if N equals 0.2 lit. Cool. Just living long line 9 now. it's it's marginally better than having to write this everywhere, right? The 2 lit, or not 2 lit, but the mask everywhere after every addition. But it does mean our operations are all slower. But I think that just has to be the case. Okay, now it doesn't even run. Oh, interesting. It ran fine from 0, but we couldn't skip ahead. Okay, 0. Let's make that 3,000. Weird. Do we see why that's happening? Huh. Oh my god. Hmm. Well, here's an idea. I could let that run in the background while I do the vault puzzle. It's the JVM. The JVM has always been cursed. But you knew that. Do I have anything to do with native Scala? Do I do anything with natives? No, I've never I've played around with it every now and then. Um Basically at this point I would only use it if I want to do like bare metal interop or like interop with C programs or something, or if I just wanted fast startup time. That's the main benefit in my eyes. But then you also have Graal. You could also just use Graal VM for that and do like do a native image. Um, but here's the thing: the JVM is actually pretty fast. So I've done a test where I had like a huge prime number generator. I optimized it as much as I could, ran on JVM and ran it on native. And for like small numbers, native would look faster because it doesn't have the JVM startup time. But once I got to large numbers, the JVM's like hotspot, whatever, all that's runtime optimization was a lot faster than native. Hmm. And now we're up to 4,000. Interesting. I don't know why that just Stack Overflowed right off the bat. Maybe it's because of the memo or something. Okay, in the meantime, let's at least finish the game. Um, so I also am ready to do the Vault Challenge. I should change my memo not to include the R8. Yeah, I could do that, and then I could just clear my memo every time I run. You know, that's fair. Right. So let's take that out of there. Yeah, it's storing a lot. And then on every loop, I do a memo.clear. So here is the for one, and then we do memo.clear, and then run again. So that got to 6,000. So that got to like 2%. And you know what? I'm only gonna print every 100 or so. If R8 mod 100 or mod 1000, let's just do every 1,000. No, we want to see more than that. 100 equals 0 dot 2. Wait, R8 dot int 2 int mod 100 equals 0. Then we do this print line. And what's the issue here? The value is now a member of Boolean. Uh-oh. Mod 100. Hold on. Oh, then, I see. Okay, now it's actually moving faster. So print line actually slows things down quite a lot. Yeah, there we go, there we go. Print line is pretty slow. We'll make it mod 1000. Or you know what? We don't need to see it. We don't need to see the progress. 5, 6. That'll take 5 minutes, I guess. Okay, that'll take about 5 minutes. That's very viable. I think we've got it. Let's just remove this altogether. Hash collisions. Oh yeah, there are gonna be a lot of hash collisions, aren't there? Because for each of them, we probably go through. We probably fill up the whole 15-bit space. Ah. So we have also got the vault, which I fixed. Okay, so this end state here, what I had done, so my intent here is that if we're end, uh, wait. So if we're end, we're fine, but we don't want to be at the end position if we are not actually the end state, right? So bad copy, you mentioned this. I think you'd had like a similar bug where you're just not getting to the end. And the way I'd written it trying to do like an implication. So like that's, not I don't know, there was like some equal here and then and and equal or whatever, right? It should have been and not equal. So basically what I was doing was filtering out the end state exactly. So I can run this now. Run main synacor.volt. And there's my solution. I posted the diff in Discord. Yeah, it was it was just unequal. A double equals needed to be a not equal. Um, yeah. So I've been waiting to do this. Um, I didn't expect it to be like nearly 5 a.m. when I'm doing this, but here we go. Let's run main synacor.main. It's 15 minutes away from 5 a.m. So we're in the vault lock. Wait a second. We'll put this there. We'll put this there. We'll put that there. Cool. I think I can just take this and like copy paste, and that should do it after I take the orb. So first we take orb. Oh, hold up, hold up. Where's our main? We're going too far, too deep in here. Yeah, this solve vault is not what we want. We could just replace the solve vault, but I'd like to walk through it. This is still running, but it seemed like, I don't know, 1,000 per second. We only have to get to how much? I always forget. 32,000? Oh, wait. That should take 30 seconds. It never finished. Fuck. Okay. Let's go to Ack and we need an upper bounds. Well, that and R8 is less than or equal to 0x7 FFF.2 lit. R8.2 int is less than or equal to, we'll do it that way. Um, we should give the proper ends here because we don't want lying to us. Oh, whoop, 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 whoop. Okay, so here's the Ackerman. And once that finishes, I guess in about 30 seconds. Right, I don't know, I was thinking 300 seconds for 5 minutes. Well, we'll see. So we go back here, and we want these. So let's go back to main. I'm just gonna paste them in here. Commented for now. And there are few enough of them. I'd like to walk through them. So we take the orb. Oh, hold up. Our IO is messed up. uh, yeah, never, never trust code you've written after 3 a.m. Yeah. New client connected? Shutting down client. Oh, okay. There is another SBT on this build, so we're sharing the same server right now. You know, I think I should be fine with that printing every 1 second. Well, we'll start with this. I'll keep leaving that run. So take orb, and we go north, east, east, north, west, south, east, east, west, north, north, east. As you enter the room, the orb briefly flashes red. The number on the oh, we're too big. Undo, and then we go east. Nope, we're gonna undo again. Frankie, hello. Good to see you. So we go east. Here we go. Now the text size is right. As you enter the room, the orb briefly flashes red. The number on the floor vibrates strangely beneath your feet. The orb seems to get lighter. As you approach the vault door, the number on the vault flashes white. The hourglass is still running. It flashes white. You hear a click from the vault door. The orb evaporates out of your hands. Huh. All right. You stand before the door to the vault. It has a large 30 carved into it. This is the same old description, so we can just go into the vault, yeah? Yes, this should be the... we're very close to done. We just have another thing running in the background here, which I don't think is gonna complete. The vault. This vault contains incredible riches. Piles of gold and platinum coins surround you, and the walls are adorned with topazes, rubies, sapphires, emeralds, opals, dilithium crystals, Illyrium 115, and unobtainium. Okay. Things of interest here. There's a mirror. So let's just take the mirror. Look, mirror. This is a rather mundane handheld mirror from the otherwise magnificent vault room. What use could it possibly have? Use mirror. You gaze into the mirror and you see yourself gazing back. But wait, it looks like the mirror, looks like someone wrote on your face while you're sprawled unconscious on the beach. Through the mirror, you see a code scrawled in charcoal on your forehead. You've reached the end of the challenge. This is almost certainly the wrong code because I haven't set R8 to the right value, right? So I mean, I could try it just for some, and my codes. So FA5, FA5. Yeah, that's not it. Um, well, I don't know. FA5. Yeah, I hope it depends on R8 because that's the only. Did it say R8 was accessed? I never got a notice that R8 was accessed. Reverse the string because it's in a mirror. Oh, okay. Yeah, totally. Um, Reverse. Okay, let's try that. 9DC064. 9DC064. Nope, that doesn't do it either. It was worth a shot, definitely. And once we get R8, we're gonna have to try both ways. Okay, so let's look at our history. That is our full history. Um, let's take this stuff and we'll copy it into our editor. I guess some of it is already there. You know what? Let's make this a volt solve. Okay, so then now solve volt equals that. And then we could leave the mirror to after that. So this. Okay, so now when we start up again, we should be on the other side of the volt. Um, Found index. Oh, wait. What do we have to do? This bit here, split and to list. Did anyone watch Antheon? I watched it in this last year, and it was fun. It was a fun show to think about. It's about like uploaded intelligences and consequences of that. So there is back to Ackerman here. I'm gonna go back to printing every 1000, and let's see what's going on in here, because the fact that that's not even shutting down is kind of concerning me. Oh, that's not what we wanted. Run main Ackrun. The letter, well, the thing is, did we, huh, so the code only uses letters that can be mirrored. You're right. LWLOIXAB becomes D, VXH. Right, yeah. I figured, like, my gut instinct was like, it wouldn't be worth it, or like, it wouldn't be the case because this was a hash of some sort, but I guess it's not a hash. EDD. Nope, that's still not it. Yeah, lowercase b becomes D. Wait, hold on. No. We have to do this, and then B to D. 9F7. 9F7, AB4E. Ah, there it is. There it is. Um, I would have got that eventually. I would have had to think about that once I got R8 and saw that, oh, well, look at that. So we made it all the way through once. We've made it all the way through several times, actually. Why are we not stopping? Because we never hit max value. I see. I see what's going on. We never exceed max value. Less than max value? Um, yeah, let's do less than max value. And if it's nothing else, then it's going to be max value. But I don't think it's going to be max value anyway. We can gamble on that. Um, well, there has to be something wrong with our implementation then. Well, if I take out my R3, my 3, nope, nope. We're only optimizing 1 and 2. 0.2 lit. Rev. Oh, okay. What is TR? Translate. Okay, so you translate B to D. I did fix the 2 case. Yeah, that should be correct now. And I tested it. Oh, hold on. Why does that give the same value? Interesting. Um, well, at least we can get through all the values. Let's do some tests again, I suppose. Uh, we'll check our 2 case because our 2 is our biggest optimization that matters, right? Oh, these are lits now. Dot 2 lit. Dot 2 lit. And this 2 is only working on integral type, and this is not an integral type. Dot 2 lit. Dot 2 lit. So we're going to do that dot 2 lit here too. 2 lit is not a member of int. That should be coming from here. 2 lit is absolutely callable. And let's take that underscore out. Okay. An extension method was tried but could not be fully constructed. Synacor numbers 2 lit failed with found lit required int. Something is already a lit. Oh wait. This function here is actually only on ints. Right. Okay. Yeah, so that works. So my 2 case is working for that at least. I could try for bigger R8. So I'll do 4. Yeah, I'm pretty sure my 2 case is working properly. Here is a do all the crazy things program. Delete, squeeze, replace characters. Um, you know, I learned somewhere that this is actually a command. So like I get, or that's actually a function. You probably know that, but yeah, I thought that was funny. What looked like syntax was actually a function. Um, Bash is being Scala there. Okay, so that's not the issue then. Is uh is the overflow the issue? The overflow shouldn't be the issue. The overflow is like the solution. It's necessary. What else is sketchy about this? I mean, other than these two, it's straightforward Ackerman, right? We're recursing. We're passing our R8. Our -1 is plus that. And that should be working like as expected. Times n. I'm pretty sure our times is fine too. Right? Like this would have been tested in the power on self-test. So I don't think that's the issue. So I'm not sure what gives. Let's take a closer look at this code here. We're not doing anything weird. 4, 1. We're checking if that equals 6, right? Well, not ends equals 6. I don't know, like maybe we're, if ends, I don't think we even need to mod it. We don't need to mod it, right? Equals 6 to a 2-lit. Yeah, let's just do that. Not found ends. What do you mean not found ends? Oh, we need to uncomment the base case. Oh, that's the wrong one again. Did this never compile? Oh, right, it's just starting with this previous code. Halfway there. 26,461. You know, how long did I spend trying to get this 3 case? That was probably like a good hour or two, right? I suppose I should have tried this already. The 2 case. I saw it was already faster. Okay. So we completed a run. Is my one case accurate? If my one case was not accurate, then this wouldn't be working. I just want to see the first case. Oh, mod 1000 equals 1 is what I want to see. Three two seven six five, right? That's the one we've been seeing. That's well known at this point. And we could even do that. 2 hex string 7FFD. Yep. Would there be something preventing us from what could it be? Okay, so what kind of weird things can happen? Could it be the overflow? Right, like how we basically expect to get there. If it's a 4-1 case, it's gonna be a big number. So we basically expect to get there with some sort of overflow. But the only things we're really doing, well, the only things Ackerman really does is like subtract 1 or plus 1, right? So the overflow happening there is always straightforward. Here, we do actually have some multiplication going on. Like maybe it's worth looking into that multiplication. We are adding values greater than 1. So like, we should mask what I mean we're already masking, right? This plus masks. And the multiplication masking doesn't lose any information in the lower bits. Right? The higher bits could not possibly have any sort of effect on how this is supposed to run. And as int is 15-bit, the biggest we can get is like 30 bits. So we don't have to worry about our host integer overflow either. So it's not integer overflow. It's not a lack of the U15 masking. Right, integer is not going to overflow because we already overflow at 15 bits. So the multiplication is safe. Okay. What else could it be? We are so close. Hmm. I'm gonna take that out. Mm. We can't really do testing against our naive ACK with m greater than 3. 2 is pretty much our limit there. So I don't know. I really don't know. Our checking here is very explicit, right? Ands equals 6.2 lit. Yeah, sure, I could dump them and have a look. Yeah, giving ACK4 equals, sure. Um, let's see. I can do that if I do like an SPT. I pass run main Synacor dot Ackerman. Right, and then I can pipe standard out to Ackerman. And I can take out this if and just print line every time. Okay. Give that about a minute. Um, yeah, I suppose there's no need to keep running it over and over. Well, that's like your normal mode of operation, right? Is like you're always to a file or bad cops. This is perplexing, isn't it? Like anyone looking at this would be perplexed. Now we are being like, obvious bug. Yeah, I like that shell widget too. I complimented her and she's like, oh, this thing? This is my thing. Oh, okay, it's done. So last Acron. Oh, we got all the info. I thought this went to like standard error. That's a little bit annoying. But whatever. Okay, so oh shit. We want equals 6 and then end of line. Pattern not found. Okay. Or maybe we want let's just do equals 6. Here are things that start with 6. It happens, it seems like it happens actually less than 1/10 of the time. I was gonna say it happens about 1/10 of the time. Um, Bad cop. Is this a regex when I do this search here? If I do equals 6 and then dollar, that should be end of line. I'm doing that right? Because it's not found. Yeah, that's less. And you know what? Let's pull that up into um let's pull that into Scratch. Or hold on, we can find Ackerman. Here we go. Try it with something found. Random. Oh yeah, you're right. You're right. Good call. I don't need to ask. We can figure it out ourselves. So we could do like equal 9861 dollar. Yeah, it finds it. Cool. Less is regex. Great. And you know what? In fact, that's found twice. So there are some collisions. There are collisions all over the place. They're just not colliding at 6. Is there anything that's even 1 digit? Um, let's do that. So equal space, just a dot, and hey, we can get 5. We can get 5 again. We can get 3. We can get 9. Suppose I have like an off by 1. We can get 1. Interesting that we get that for 2 adjacent values. Interesting or suspicious? Huh. Okay. The value we want is 6, right? We know that. We're pretty sure about that. Yeah. After the call, it should equal 6. Call Ackerman. Calling it with 4 and 1. Um, okay. I'm like one tiny bug away from being done with this. I want to get it. Okay, good to know. Oh, sure. Yeah, I'll push my code. Mm, big blob coming in. Almost done with Synacor CC. I'm gonna force release. Okay. Oh, wait, did I do a little I don't care. I'll live with it. We're forcing. YOLO. As recognized by the regular expressions library supplied by your system. So it depends. I think it'd be cool to be a regex pro. Is there like I don't know, an advent of code for regex? Or, a leak code for regex where you can just practice regexes all day? Mm. I bought the book. It was one of those O'Reilly books, Mastering Regular Expressions, some time ago, and then I lost it. Mm. By some time ago, I mean like over a decade ago. Um, before I even entered the industry, I was gonna master it and wow people, and I never did. Um, I don't know. At this point, there's no way our Ackerman is wrong, right? Like, it's all right. Scala here. We are not missing these cases, or otherwise, like, it wouldn't be fast, right? So, all right. I guess now we could do tests with things that are larger, because you know what? A lot of our failures earlier were the integer overflow, and probably the reason I thought things worked was because I had my act lit function. I'm gonna have to rewatch that VOD and see what's going on in there. Um, biggest issue is probably that it's 5 a.m. You can use regex in all your search and replaces in Emacs. Meta shift 5 will do that for you. um, I noticed the other day. Nope. Oh, here. No, okay, you can use regular expression for search. Can you match groups and then replace the thing in the group? I'll have to try that sometime. Yeah, I guess VS Code has it too. I complained about that for a while, and I realized, oh, it's actually right there, not regex. I don't know. I haven't messed with it. You've done horrible things with it before. um, I've done horrible things with sed. Like I've done like code base wide um, updates with sed. Xarg sed. Um, Scala actually has a nice static um, code updater called Scala fix. And like sometimes like a library maintainer will add like a Scala fix rule that modifies your code, and it works on the intermediate representation, so it has everything and all the types and everything, and it can do all kinds of different fixes. So you could use it kind of as a linter to your code that is compiler aware and fixes your code, fixes common issues. Um, With LSP support, find and replace scares you because if you do it with an LSP server, it might blow up. Or I haven't actually talked at depth with anyone that uses Claude yet. Although, what is that? What's that? Well, I was talking with this client that I'll be working for in January. They asked me if I was familiar with Cursor. It says apparently they have a corporate subscription and use it there. So I might get to meet some vibe coders soon. Um, yeah, I'm gonna keep staring at this until I get it. What could I possibly test? I don't have like a lot of references to test against. I suppose I could convert this act to an actlet. And I could test against that for some values. Yeah. Yeah, that will allow me to test with bigger values, right? Because we won't have the overflow issue. So let's do that. Next rename to actlit. Great, and we're gonna replace these ints with lits. Int with lit. Up, 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 up. That's all we need. Cool. These up here. So we can make these m and n again. M is equal to 0.2 lit. And this case here is n is equal to 0.2 lit. So at least let us check, I think, the three zero cases. Oh. We have m and we have n. Great. That 2 lit here. Plus 0x7fff dot 2 lit. I wonder if I should subtract 1 as an int, like 2 int, and then convert back to lit. 2 int minus 1. It should never go negative, right? It'd only go down to 0. I don't know. We can hold that thought. If someone thinks it's gonna do anything, then let me know and I'll try it. So plus 0x7fff dot 2 lit. I guess converting back. Actually, it wouldn't even. No, the performance wouldn't matter at all, actually, because lits are ints. Yeah. Okay. Whatever. This is why having a language that compiles step is nice. You can just change the definition and use the compiler final braces that broke. Uh, yeah, totally. Oh, right, right. We were talking about LSP can understand disambiguate otherwise identical references. Oh, right. Yeah. Is LSP smart enough in like Python to be able to find and replace correctly? My case 2n is different from yours? You mean my code is different from what you have? Um, oh, you're using a different expression. Yeah, I had a different expression here at some point, but it was bugged. So instead of trying to fix it, I just went back to this expression, which I'm happy with as long as it works properly. So we're going to test it against this actlit. So 2.2 lit n.2 lit 4.2 lit. Okay, so we'll run those tests. Here we have something. Oh, no, we don't want to print anything. You think it's wrong? You think yours is wrong? Oh, your test suite fails it. It looks right, though. Okay. I don't have much of a test suite, but that's part of why I made this an ACLIT so I could test other things. So I'm going to look at, look for some failures here. Let's drop this back to something like 2. And let's go to 3, 0. And what values do we get? Oh, it's taking a while for ACLIT is taking a while, isn't it? Let's max out at 5 then. 0 to 5. Okay, yeah, those are different values at a 3. Cool. Well, we found an issue, and it's not in the 2. Um, interesting. Okay, I find that's weird to me that the 2 would work. This test would pass, but not if I went up to 3. Let's think about what actually happens then. So, okay, let's see what you're saying here. The compiler is always your final source of truth. You need a really good reason not to use it when available. Fair, fair. Okay, so one true Bob, you have R0 in range 1.3, R1 in range 1.6, R7 in range 1.10. For R7 in range 1.10 and compare that with the 2 functions. R0 goes 1 to 3, R1 goes 1 through 6. Okay, yeah, and my 3s are... I could compare those full ranges. I think the 1s are fine. Let me comment this bit out. We can just test them one at a time. That's enough for me to believe. And I know that making this bigger, R8 bigger, is just a constant factor, so I'm not going to bother testing that. 3 though. 3 is worth the look. Okay, how far off is it? The source of truth is the first one. 1138, 119. Let's pull up our worksheet again, where we were developing this. Okay, and how did we get to this case? Well, actually, okay, this is what... Bob, is this what you have? Because that's actually what I kind of ended up with when we... Okay, so for R8 equals 1, this you get from Wikipedia. You get 2n equals 3 plus 5. So for an R8 equals 2, I believe this for R8 equals 2. So I could just test this, make sure that works. Um, 3 times n plus 5. 3 times n plus 5. This should give me 3 times n plus 5, actually. So we'll try that for the 2, 0 row. And then I think I need to try that again with 3s, because 3s reveal some bugs in m equals 2 that I hadn't noticed. Let's just do a guard here so we don't mess things up. R8 equals 2.2 lit. All right. So we'll special case that up earlier. And in this case, we have 3n plus 5. Yeah, we're not doing this in terms of R8. So 3 times n plus 5 2 lit dot 2 lit times n. Okay, so we're going to test with r equals 2. And we can test other values, I suppose. And does that even work? Nope. Okay, so that we need to generalize properly. But, where there's a 2. Yeah, I don't think I ever had anything that was working there, actually. I have something that looks like it works. Um, well, we know 2n plus 3 for sure is a thing when r8 equals 1. And how do we math to that conclusion? When r8 equals 1 here, I don't know, it's like a normal Ackerman. What happens when you increase r8? Why is the 3 case different? Let's look at expansions. Of 3. I want to see expansions of 3. Values of a, m, n. I'm not sure what this table is. The value is replaced by the relevant expression from the function to show the pattern clearly. Okay. So a0 becomes a21, right? If we have m0 and if we have n0, so m equals 3. 3, 1 does this. We go back up to 3, 0. We do 2, 5. I am putting faith in the 2, 5 bit. Why would the 2 look correct, but not the 5? Why would this look correct when it's 2, but not 3? Like, what happens different with 3? Are calls to this different? Does n, like, get significantly larger? Like, we could... Well, we could take this to 20. I don't want yours. I do want to figure this much out. I'll take your 3 case when I'm all done with this. But this is the last piece I need to figure out to get this. Um, is it just that it doesn't work when R8 gets big? No, 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 no. It's already failing to work. Function we're building off of is 2n plus. Wait. 2n plus 3 equals. Oh, they're giving two different expressions of this. So I could have said 2n plus 3, or 2 times n plus 3 minus 3. 2 plus n times plus 3 minus. Oh my god, what if we just follow that same pattern? Oh, well, actually, no. Yeah. 2 to the n plus 3 minus 3. Okay, so how did R8 generalize then for this case here? So for the one case, um, let's see. If R8 equals 1, it's going to be n. It's got to be n plus 3, right? We got this row up here. 2 plus n plus 3 minus 3. Right, so 2 plus plus 3 minus 3. And that, so that should expand. This expands to, if R8 equals 1, this is n plus 2. And this would also be n plus 2, because we have plus 3 minus 3. Right, n plus 2. Cool. So I'm pretty sure this is generalized correctly. Well, actually, I'm not even sure if this is generalized correctly anymore. But I do feel more confident in it. So what analog with R8 equals 2? R8 equals 2. This would have to be 1 greater, right? So there's a plus 1 in here somewhere. So where do we fit the R8? And can we do a similar thing with this here, with the multiply? Two times n plus 3. Oh, wait. Yeah, 2 times n plus 3 minus 3. The R8 doesn't belong here. So we have, I don't know, if R8 is equal to 1, 1n is good? Okay, thank you. Yeah, save me time to that rabbit hole. R8 equals 1. Yeah, when R8 is equal to 1, this is 2 times n plus 3 minus 3. And we need some new fun. We can bring ourselves into like guess and check territory, I suppose. Um, I feel like figuring out why 30 brings out that difference, but 20 doesn't, would help me figure out this issue. Oh. I suppose I can. Well, we know what values we're supposed to get when it's one line further, right? So let's look back to that. Da, 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 da. So 0 to 5, and we're doing 3, that 2 lit. And how far off is that? When we call 30, whoops. I'm gonna put my code on the left. Okay. So 30 is already wrong, right? So what does 30 become? 30 goes to, oh, sheesh, equals m minus 1, so like 2, and then we recurse with, yeah, let's put the a here so that Copilot isn't trying to steer me wrong. A, and then on the inside, 3 stays there, and we subtract the other side, n minus 1. N minus 1? No, 30 should hit a different case altogether. Let's hit 3-1. Yeah, 30 hits a different case. So 3-1. Let's do that. Actually, it's interesting that the 30. Okay, what happens in 30? Actually, let's look at that. If n equals 0, so we recurse here. Yeah, let's look at that. 30. That's worth it because even 30 is wrong, right? So let's look at our recursion. That's this case here. We act with 3 minus 1, so 2, and then 1. That's what's supposed to happen, right? I just want to see an Ackerman. Right, 1. Where the 1 becomes the 8. This case here. So 1 could be 8 or something. Whatever R8 was. Oh, there it is. There it is, right there. There's a bug. We forgot to do R8 right there. Found it. Found it. Yeah. Yeah. That's so this function is fine then, I think. It's well, that's certainly a bug that matters, right? That's certainly a bug that matters. So let's run that. Da, 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 da. Oh, we started adding a bunch of other code in here. Let's get rid of that. 1.2 lit, 2.2 lit. We have our special cases, great. When we were recursing, we are doing that R8 bit. Oh, you know what? If I tried R1, I would have seen it working properly for R1, probably, right? If we do that. But then that doesn't mean like we've not generalized or something. Okay, get that out of there. Cool, cool. It's working properly now. Great. Well then, let's do it. This is the moment of truth, isn't it? Ah, hold up, hold up. Moment of truth is another Stack Overflow. Uh, what's going on here? Don't do this to me. Uh, okay, what could it possibly be? We are memoizing. We're clearing the memo. Are we clearing the memo? Cool, cool. Um, I mean, that sounds like the overflow thing, except that these are all lits now. All right, so it's gonna be less than whatever. And we're gonna go back to MN case. So like the 3 case, it can go to 2, 1. I guess we could look for the first R8 that gives us a problem. It fails so fast though, really fast, which makes me think of like the stack overflow or like the integer overflow issue. But we can't be negative. Lit is non-negative by definition. I shouldn't need bigger stack params, but okay, let's do it. SBT here. It's in my build.sbt too. Yeah, no, we're having the same issue. You had to increase the stack size for Java. Still? Okay, well. 16. We're at 16. How big can you go? You know, we're doing 512. 512. Hey, it's in my build. Just to be extra. Oh, you know what? This is saying 1024. I wonder what overrides. I think the build probably overrides. Ugh. There we go. There we go. It's running. Here's the moment of truth. $14, $15. We're halfway there. This loop better end. Please end. I need to sleep so badly. No. Ah, yes, we got it. We got it. Cool. 25734. That's our thing. That's a number. Okay. I'm gonna make sure that's saved here. And now it's time to mess with shit. So let's go to our main. And here we can do our big number. Dot to lit. Nope, nope, nope. We'll do that. We'll do that by hand. So we're gonna we take our shortcut and we're gonna stop there. And we'll set to register ourselves. Okay, here's the real moment of truth now. Okay. So what was our value? Oops. So we're gonna set R8 to this value. And then we're gonna use teleporter. Okay, we wake up on a sandy beach, we find a message there. And we sum that. And we check that. 797. Oh, where is it here? 797 ending in A2A. That's it. We got it. Ah, about damn time. Okay, cool. Let's commit this. Thank you, thank you. Thanks for sticking around till the end. That's exciting. Man, what a trip. And I'll push that. And there we go. If anyone wants to see, there's the repo. Oh, right. Time for the vault. I suppose I could go to the vault. I mean, we already got the code from the vault, right? And that worked. Why not? Let's do a victory lap. We have to get all the way to the end. So, from the beach, we go north all the way. It did work, right? So this code here, where I took the mirror, 9F7 AB4E. That is down here, 9F7 AB4E. So we got it. But I don't know. This might be the best closure, is actually just running through north, 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 north. Yes, you must be using the, oh crap, the other binary. Um, Wait, volt lock, we're in a grid of rooms. Oh, oh, south, 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 take orb, and then we need our volt path. So where is that? That's in here somewhere. Volt.scala. I think I put it in a comment here. Yeah. No, that's not it. Okay. We'll look at main.scala. We have it there. So solve volt. Northeast, east. Northeast, east, north. North. East. East. North. West. South. East. East. West. North. West. North. Northeast, east, volt. Northeast, east, east, volt. North. East. 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 Oh, shit. Crap. Oh, wait, volt. There we go. Um, Take mirror, use mirror. And we get the congratulations message. You have reached the end of the challenge. And that was our full command list. Too many norths, too many easts. Yes, yes, get code. And, we can do this again. You know what? We're going to echo that into rev. Into MD5 sum. No, just into rev. And then we're going to echo this into MD5 sum. MD5 sum. Because we need to take the B. And I'm not using TR. Oh, wait. What? That's different than we were getting earlier. Oh, right. We didn't actually... Where's rev? Echo that into rev, right? Then we can echo that into MD5 sum. Or, I don't know, hold it this way again. Oh, I see there's a backtick. Well, let's do it let's do it that way. Except the B needs to be a D. And there's our code. Cool. Officially finished. Officially finished. Oh yes, and I'd love to see your repo. So thank you for sharing that. Anyone who has a repo, send me the links. Zuno, could you drop yours? The one with the explanation. Be happy to see everyone's. And I'll probably move mine into its own repo eventually. There are still other things I want to do with it. Like I want to make a nicer emulator still. I'd like to put it in on a browser. Um, Synacor challenge solution. Okay. And one of the things I might do is take it and use it to implement the Jack VM. So 9 to Tetris, there's the Jack language which runs on the Jack VM, which is a stack-based VM, which then you can implement in terms of assembly. But like this could work there, right? Like this Synacor VM is almost an assembly, whereas this is a little bit higher level. And in that case, I could use the Jack compiler to compile programs down and to run in like Synacor, to like Synacor bytecode. Um, so that'd be cool. I'd have a way to do that, and this would be the easiest way I could do that, I think. Just because this is so simple. So that's a thought perhaps for the future. That in a browser version. I might just revisit Nan to Tetris altogether. Um, I've got this book. Got it open right now. There's a second edition made in 2021 that they've expanded. So I might buy that, go through that book, and revisit this as part of a stream series. And in that case, um, I could do everything updated. I could make my own emulator. Um, right. So they have like a PC emulator that does like all the I/O and stuff like that that you would run your compiled bytecode on. Um, but it's not satisfying because you didn't implement that yourself. Like you implemented a copy of it in terms of just like CPU architecture. You ordered the book? Oh, cool. Yeah. Highly recommend this. It's very well loved by a lot of people. Um, yeah, like anyone who's enjoying this in the core would totally enjoy this book. Um, yeah, and I thought it was just really, really elegantly simple, like simplified. Like the hack machine specific, like the hack machine language. The way the opcodes are organized, I thought was really cool. And yeah, but until then, I'm probably taking mostly a break. I might stream something easy, um, something that's not ever going to keep me up until 6 a.m. Like maybe 3 hours doing, uh, what's the game called? A Zachtronics game. I'm thinking about doing Shenzhen IO. Then it can be more relaxed. I can be more chatty, um, and still have like a fun puzzle in front of us. And like it's got wires and stuff. We could all look at that. But thank you all for sticking around through this. I'll I'll keep you all updated, but I might do at least, at the very least, a weekly Monday night stream, and we'll figure out the rest from there. So let's find a raid. Man, that's a. I was having Synacor dreams. This background music I've been playing, I started dreaming about it. Oh, nice thumbnail. Yeah, I'll absolutely make a write up. There's kind of two kinds of write-ups I want to do. One is just like on solving this, and then another's like on my process, including my mistakes and what took so long, what went fast. Um, because I'd like to analyze my problem-solving process, and in doing that, I could hopefully improve it. But a write-up to start, perhaps, and then turn that into a video. I'd like to make YouTube videos someday. I'd like to go into the light chess stream, except, you know, he doesn't really interact, right? Like, I'd like to hear him talk about the code a bit. This is like the biggest Scala stream. um, Revolutionizing compilers. Westlang, NixOS, cool. Yeah, someone doing compilers sounds cool. Oh yeah, I see Europeans in here for sure. I'm gonna start becoming familiar with them if I keep doing this. 3 hours, 3 to 4 hours is about my maximum, and then my brain starts farting, and I think you can see it. Be right back. Oh, we can't raid you while you're gone. We'll give a follow. Dima. Did Dima just leave? I am Merlin. Is the one that left at 6:15. Hmm. Maybe someone else can tell us about the project. Not even 19. Oh, just straight up playing chess. Yeah, well, we'll see about that when Liquid Cake starts screaming. Every December. Every December. Next year after Advent of Code is done, I need to pick something that won't keep me up this late. For my first few streams of Synacor, I was keeping it to 3 hours. Um, and then Dave and Bad Cop finished, and I was like, I have to finish too. I should stay up all night. Also, it's like getting to the end of the month. I want to be done by Christmas. Hmm. How did your exams go, by the way? I remember you were talking about that a few times. Compiler, dev, there's a Solitaire app in Godot. AI agents. We could talk about AI agents. I don't know. I don't know. I'm kind of tired of talking about AI. Yeah, I have no idea. Yeah, totally. More time means more enjoyment. Yeah, if you're taking shortcuts, then you spoil it for yourself. More data science courses down. Nice, nice. Um, well, you know what? I'm gonna go ahead and initiate a raid for Infinite Coder, and that's where we can go when they get back. Oh, they're back. Raid in Infinite Coder 01. All right. Good night. Thanks for being here.